So,
Hi, Shalabh. How are you?
yeah, I'm fine. So, okay. Yeah, you are audible. You are pretty audible. So, we just wanted to.
Okay.
Can you just share your slides once so that we can see if they are coming fine?
Yeah, let me.
All right.
Yeah, let me see. Select the window screen. Is it good?
Yeah. That's good. That's good. That's good. Okay, we'll get
Okay.
started at
Wonderful.
9, which is
Okay.
about 7 minutes from now.
So should I leave it like this, or should I stop and then connect again?
Uh, no, you can leave it as is.
Okay.
It's better to leave it as is.
Yeah.
So we'll,
Okay.
yeah. Sure. Thanks
Sounds
so
good.
much. See you in a moment.
Thank you. Sure. Yes, I can hear you. But that's fine. Let's have it in between. If it's a long one, I can ask to continue at the end. Sure.
Yeah, sure. No, I just wanted to ask if you wanted questions in between. Yeah. What does this camera do? This camera turns on this camera? Yeah, okay. So, yeah, hi Mohammed. This is how I am.
Hi, Prashant. How are you? Good to see you.
I will wait for a couple of minutes because it's not 9 o'clock yet. Yeah.
Sure.
How are you? How is Amazon? So it's a public forum, so you may want to keep your responses polite. Yeah.
Yeah. So things that's very much focused on Gen AI, everything these days. So at companies is there's a lot on that.
Mm.
Yeah.
Can we get started or we can get started? Okay, hello everybody. Welcome to day one of RL workshop. It's technically day two, but this is the day when the research talks start. And I'm happy to introduce Mohammed Kamzadeh, who's been a collaborator from not so distant past. Mohammed got his PhD from UMass in 2005. He was a postdoc in University of Alberta from 2005 to 8, and he was a permanent researcher at India from 2008 to 2013. And about 2 years there, I did overlap, and incidentally, my first ML conference submission happened with Mohammed, my most successful ML conference submission. So, in case you want ML paper, you should consider working with Mohammed. He was the recipient of Indria Award for Scientific Excellence in 2011 and obtained his habilitation in 2014. Since 2013, he has been a research scientist at different places, starting with Adobe, Facebook AI Research, Google, and now he's in Amazon. He's published over 120 refereed papers, and I'm telling you that's a lot. It's very difficult to get ML conference papers. You can take it from me. And he's co-chaired more than 10 workshops and tutorials at NeurIPS, ICML, and AAA top ML conferences. And his research, it's obviously in the area of reinforcement learning, bandit algorithms, but he also looks at recommendation systems, and more recently in the most popular trend, which is generative AI models, he has been looking at problems of alignment and complex reasoning. Thank you, Mohammed. Over to you. Yeah.
Thank you, Prashant, for the introduction, and thank you for the invitation. And sorry that I couldn't be there in person. Good morning, and it's evening here, but good morning to you in India. So entropic risk optimization in discounted MDPs is the title of my talk. And this is a joint work with Jia-Lin Hao and Marek Petrick at University of New Hampshire and Eric Delage at HEC Montreal. So this is the outline of the talk. I give you a little bit of preliminary about risk neutral and risk averse RL, and tell you a little bit about the popular risk measures, especially those that we are using in RL. And then I'm gonna focus on entropic risk measures and talk to you about MDPs with two entropic risk measure, ERM and EVAR. I'll tell you about their properties and the results that we have obtained about them. And then we have some numerical evaluation. If time allows, I tell you about risk-averse soft robust MDP, which is the combination of risk awareness and robustness, in which both aleatory and epistemic risk play a role. But that's the optional part. Let's start. So the first part, I'm telling you about MDPs just for probably you already know about RLs. I just talk about MDP very quickly to set the notations and that you can follow better the rest of the talk. And then I'll talk about risk neutral and risk sensitive or risk averse MDPs. Let's start with MDP and risk neutral. So MDP is this tuple of states S, actions A. These are the state set and action sets. The reward function, which is a mapping from state and action to reward functions. I use delta R as the range of the reward function in the talk. P is the dynamic of the system that maps a state and action to a distribution over states. S0 is the initial state of the system, and gamma is a discount factor that can be the 1 for undiscounted problem and can be less than 1 when we are using discounting, which is a very popular setup in MDPs. I use capital T for the horizon of the problem. So whenever the problem is infinite horizon, the T, you can consider that T is infinity. And when it's smaller, then we have a finite horizon problem. So in infinite horizon problem, usually we set up the discount factor between 0 and 1 in order to make sure that the return random variable remains bounded. And when we go to the finite horizon, then we usually set the gamma to 1. So then policy in general is a set of policies at each time step t, which maps states at that time step to a distribution over actions. This is a Markovian randomized policy. So clearly, if we map a states instead of a distribution over action over just the over actions, not a distribution over action, then it becomes a deterministic policy. And then if all the policy at each time step, all the time steps, the policy is the same, then it becomes a stationary policy. So I'm using capital Pi MR to show the set of Markovian randomized policy. When all the policies at each time are equal to each other, then it's going to be the space of a stationary randomized policy. And then if there is no randomization and the policy just maps the state to action, then we use the deterministic counterpart of this. And those are the policy sets that we use for that. Okay, then let's talk about the return random variable. Return random variable is basically the sum or discounted sum of rewards that you receive whenever you start and then you follow a policy. So this curly R pi of t is equivalent that you start from the initial state of the system and then go for horizon capital T following the policy pi, and then you receive the reward function. Because of if there is no randomness in the system, this quantity is, when I say randomness in the system, means dynamic and policy are all deterministic. Then every time that you run your policy and calculate this return, you're going to get the same number. So there is no randomness there. But as soon as there is a stochasticity in the dynamic or there is in the policy, so every number, therefore this is a random variable. And this is the very important random variable that we are going to work with. Just in terms of the notation, whenever I want to say the sum of the rewards or discounted rewards from time t to the end, I put t colon capital T. So that means I'm not looking at the entire return, I'm just looking at the return from time t until the end. So this is a very important random object that we're going to work with in this talk especially. So now let's see what is risk-neutral MDP. In risk-neutral MDP, the objective is to maximize the expectation of this random variable. And you want to find the policy such that when you run this policy and calculate your return and repeat this process for infinite potentially number of times, the average that you calculate is the maximum. So this is the risk neutral. And we know that in risk neutral MDP, the optimal policy in the finite horizon setting is Markovian deterministic, and in infinite horizon is stationary deterministic. So this is already known. Okay, then in any reinforcement learning algorithm that you deal with is directly or indirectly deals with value function, and value function at each time t is the expectation of the return random variable from that time t until the end of the run, the capital T. And then we know that we have this Bellman equation, or basically we can write the value function at each state as a function of the value function of the states that you visit next when you follow that policy. So this recursive formulation allows us to develop algorithms and solve MDPs in the risk neutral setting. And the optimal value function is has this Bellman equation, which is nonlinear and has a maximization in it. I think you are all familiar with this. This is just to set up the notation here. So now let's move to from risk neutral MDPs to risk averse MDP. But before starting that, let's say what is risk measure. So risk measure is a mapping from random variables to real numbers. I use psi to show a risk measure. So risk measures have different properties. A very important category of risk measures are coherent risk measures. Coherent risk measures have four properties. First, they have the monotonicity, which you see the definition. If you have two random variables and one is bigger than the other, you see the same thing when you apply the risk measure. They have the translation equivariance, and you see that if you add something, it's going to come out a constant. They have the subadditivity and superadditivity. So it depends on whether we are talking about maximization or minimization, or in MDP working with reward or cost, you use either subadditivity or superadditivity. In this talk, I'm focusing on reward and maximization, so I just use superadditivity here. So superadditivity here is defined, so the superadditivity is defined this way. Then the fourth property is positive homogeneity. And positive homogeneity means if you multiply the random variable with a constant, then and then apply the risk measure, you can take the constant out and apply the risk measure only to the random variable. Then we have also the convex risk measures. So convexity and concavity, again, is dual. If you're dealing with reward and maximization, you're talking about concavity. If you're dealing with cost with convexity, so in this talk, we focus on concavity. But if I use them interchangeably. Basically, what I mean in this talk is concavity because we are dealing with rewards, and this is the property. So every coherent risk measure is very easy to show that is convex, but any convex risk measure is not necessarily a coherent risk measure. So this is the important properties that we're going to use. So now let's look at a couple of popular risk measures. So a very popular risk measure is value at risk at confidence level alpha. So value at risk at confidence level alpha is basically 1 minus alpha quantile of the random variable, which represents the 1 minus alpha worst fraction of the random variables. Here we are talking about return and reward. You can think about if we return random, if we look at the return random variable distribution, we are talking about the left tail of this distribution. This is the bad tail. If it's talking about the cost, then we are talking about the right tail. And this is the undesirable tail of that distribution. So the value at risk is basically showing that worst 1 minus alpha fraction of the return of the random variable. Conditional value at risk is taking the expectation of the random variable in that 1 minus alpha worst portion. So it takes the random variable, renormalize it in that portion, and takes the average of it. So that's conditional value at risk. Conditional value at risk is a coherent risk measure. And alpha, which is the risk level or confidence level in both these risk measures, is between 0 and 1. So when it's 0, C bar coincides with expectation. Expectation is potentially a risk measure, but we usually consider it as risk neutral. And when alpha goes to 1, then C bar becomes like the essential infimum. So it's alpha plays between 0 and 1 in the two extreme cases. Then let's talk about the entropic risk measure. So ERM, or entropic risk measure, that we're going to talk about a lot in this talk, has a risk parameter beta. And this risk parameter is positive. See, this is different than alpha. Alpha is between 0 and 1. Beta is just positive. And this is the definition of entropic risk measure. So you can see that in the limit of beta goes to 0, ERM also coincides with expectation. And when beta goes to infinity, also coincides with essential infimum. In order to have a good interpretation, because var and C bar has very nice interpretation with respect to the distribution of the random variable. In ERM, the best way that we can, the simplest way that we can interpret mean variance risk measure. So it's exact in the Gaussian case. In the non-Gaussian case is not, but you can think of it as kind of an approximation of mean variance. ERM, unfortunately, doesn't have the this property that I mentioned here. If you remember, positive homogeneity. This positive homogeneity doesn't work for ERM. So ERM is not positive homogeneous. And that actually is a very interesting property that we're going to come back to it. So when you apply the ERM to multiplication of the random variable and the constant, you cannot take the constant out and just apply ERM to the random variable. And therefore, although it's a concave risk measure, it's not coherent. And but another property that ERM has, which is very nice, is the power property. And you probably have seen this. This property holds for expectation, and ERM also follows that property. So these two are very important, 3 and 4. We're going to come back to them soon. And then what is the entropic value at risk, or EVAR, with confidence level alpha? Again, here, the parameter that we use with the risk measure is alpha between 0 and 1, unlike the ERM that we are using beta that is just a positive. And EVAR is defined as the supremum of ERM plus a constant. So the nice property of EVAR is tightest possible lower bound, of course, in the Chernoff sense of the C bar and var random variable. So one reason that at least we are interested in this risk measure, is its relationship with CBAR and VAR. And we are hoping that if we optimize for EVAR, it could be a good approximation for optimization for CBAR and VAR. And it's a coherent risk measure. So it has all the properties of a coherent risk measure. Okay. So now, after getting to know the 4 important risk measure that we're gonna focus on 2 of them in this work, let's see what is a risk-averse MDP. In the risk-averse MDP, you are still looking for a policy that maximizes, instead of expectation of the return random variable, is maximizing the application of the risk measure to the return random variable. So we just replace expectation with the risk measure of our choice. Here, the randomness is aleatoric, is all the uncertainties coming from the uncertainty in the random variable, in the MDP, in the dynamic, in the policy, right? So this is, it's important also to know that the source of randomness is there. There is another risk measure called nested CBAR. So nested CBAR is defined as you can see here. So this definition, unlike CBAR, allows you to write a Bellman-like equation for that. So this writing a Bellman equation allows you to optimize the risk measure much easier. But the problem with the nested CBAR is, although it has a favorable computational properties because it gives you this Bellman-like equation and you can solve it easily, the problem is it's most of the time is a very poor approximation of the static CBAR. So if you look at, this is a toy example that we designed just to show that how bad CBAR, nested CBAR could be. The blue is the CBAR of a random variable at difference confidence level alpha. The red is the EVAR of that random variable for the same values of alpha. And in this specific case, they are close to each other. But green is the nested CBAR, and you can see that there is a big gap between nested CBAR and CBAR. Although it's easy to solve, it's not usually a good approximation for CBAR, which we are interested in. Of course, here you see that the EVAR and CBAR are very close to each other. In a lot of distributions, this is the case, but you can design cases that EVAR and CBAR also are not close to each other. But at least the reason that we study EVAR is we believe for many distributions is a good approximation of CBAR, unlike the nested CBAR that I've shown you here. So let me give you just this table is a summarization of properties of these concave risk measures. You remember I talked about the tower property. So you know that tower property works for expectation. It also works for ERM. Nested CBAR also has that property, but CBAR and EVAR, they don't have the tower property. Positive homogeneity, everybody has the positive homogeneity except ERM. And you see where this causes issue for us when we go for solving ERM MDPs. Okay, any question about just the intro notations and definitions? Okay, so I move on. Now we want to solve MDPs with ERM and study the properties of these MDPs and see how we can solve them. And so here I'm focusing on discounted MDPs. ERM has been studied in undiscounted and average reward MDPs. Here I'm focusing on discounted MDPs, which is a very popular formulation of MDP, and we want to study that with ERM. So the goal here is maximizing a policy, finding a policy that maximizes the application of the risk measure ERM at risk value beta to the return random variable. So here I'm searching in the history dependent randomized policy. This is the biggest set that we can search in, but then I later show you that this optimal policy actually belongs to a much smaller class. This is actually something that we show and prove in this work, but right now I just started the most general case because I don't know where the optimal policy is, so I consider a very general class. And it is also going to depend on that. And so if you want a delta accuracy, this is how you need to discretize your beta, and this is going to be the complexity of your algorithm. So what basically we showed here, EVAR MDP can be solved using the solution of a sequence of ERM MDPs. Okay, so we have done a couple of tricks to make this process a little bit easier. There are a lot of values that you can share because these value functions are calculated at different risk level, beta, beta gamma 2. So a lot of them can be shared. So there are some tricks to avoid computing values multiple times. There is also a branch and bound algorithm that you can use in order to solve this problem more efficiently. So these are what we have done so far, but maybe there are more efficient ways to go about this problem. The part that is very disappointing is this term, as I told you, is not concave. If it was concave, then the solution was going to be much easier, but unfortunately, that's not the case. So let me give you a little bit of numerical evaluation. So what I have done here in these experiments that I'm going to share with you, our goal is to optimize EVAR at confidence 0.9. And we consider that the horizon is 100 because we want to know what is the exact value, because if it's infinity, we cannot know what is the true solution. So this is why we consider the horizon to be 100. And we are going for EVAR because, as I told you, EVAR is close to CVAR and VAR, and these are the important risk measures that solving them directly is not easy. So we are trying to use EVAR as a kind of like a surrogate for them. So this is why we target EVAR in our experiments. The algorithm that we have is the algorithm that I just showed you. Evaluate the exact value. We do kind of we roll out over 100,000 episodes and calculate. So that we consider it as the ground truth. So for ablation study, we use the naive grid. So naive grid is basically, we consider beta 1 is 0, beta k is 10, and we just put a uniform grid on this interval instead of following this recipe that I showed you here on this slide. We just very naively do uniform grid. What is naive level? We are using the optimized grid, which is the grid that we propose in that theorem, but doesn't adjust the risk level with time in ERM MDP. Because we want to show that if we don't do that, of course, everything is going to be wrong and the algorithm is not going to perform very well because the recursive that you write requires adjusting the risk level, as I showed you. So if you're acting sloppy, then what is the price that we pay? So these are the two ablations that we show. What are the baseline algorithms? So of course, one baseline algorithm is just risk neutral. The other baseline that we consider is the nested CVAR. As I told you, nested CVAR is very efficient to solve compared to CVAR, but might be a very bad approximation of CVAR. We do nested EVAR, which is another algorithm that, again, when you use nested EVAR variable, you have a good, your computation is easy, but you're going to lose in terms of accuracy. And ERM 0.5 is another baseline that we have used. And also we directly solve CVAR. So I don't know if you're familiar with now, if it's the literature of CVAR, you can write a Bellman equation for CVAR, but in an augmented MVP. And that augmentation is an augmentation that suddenly makes the space infinite, and solving that CVAR is going to be that. So this is an algorithm that we used from a paper by Cho and others. So we are, in this case, we are directly trying to solve CVAR instead of using EVAR as a surrogate for it. So these are the baseline that we use. We applied all these algorithms to these 5 problems: machine replacement, gamblers ruin, 2 classical inventory management problems, and the river stream. And here, what we showed in this table is the EVAR 0.9 for the policy returned by these algorithms. And as you can see, that here our algorithm is working better than the others. In some of these tasks, the grid doesn't make that much difference. Sometimes even with risk neutral, you can get the same solution. But if you look at it over all the problems, you can see that our algorithm is working better than the others. By the way, what we make boldface in this table is when the 95% confidence interval, if the solution is within 95% confidence interval of the best policy. So this is, as you can see. Then as we said, the goal is not EVAR, the goal was CVAR. So now in this table, we take the policy returned by all these algorithms and we calculate the CVAR of that policy at confidence level 0.9, and we compare the algorithms. Again, you can see that in most of the problem, except one, our algorithm worked the best. Of course, the one that it didn't work the best, this augmented CVAR worked the best, which is an algorithm that directly goes for CVAR in this case. But in the others, it didn't work very well. Actually, we have another paper, NIPS 2023, that we showed there is a problem with the solution proposed in this paper, and we tried to fix it there. But we used the exact algorithm from this 2015 paper by Yin-Lam Cho. So this is the comparison in terms of CVAR. And then let's go to the runtime, because as you see, our EVAR problem, in order to solve the EVAR MVP, our algorithm solves a sequence of ERM MVPs. So definitely the computation of our algorithm is complex. As you can see, it's definitely more complex than risk neutral and all the nested algorithm, but it still is much, much simpler than the augmented CVAR algorithm that directly tries to solve CVAR. So if we solve EVAR using our algorithm and use it as a surrogate for CVAR, we can solve it in, 1/7 of complexity of this augmented CVAR algorithm that is out there. So all the motivation is solving CVAR is difficult. Although the EVAR algorithm requires this repetition going back to a sequence of ERM, still solving this EVAR is cheaper than solving the CVAR directly. The only question is, we don't have any theory, at least I'm not aware of any theory to show that EVAR is always, for any distribution, is this close to CVAR. I don't know. For many practical distributions, they are close to each other. But I can sit down and kind of in an adversarial way. I think that in the Borkar paper, for the undiscounted problem, there are some algorithms there. I have model-free algorithms there. I'm not 100% sure, but I think there is something. For discounted, similar algorithms can be defined, but if you want to prove whether they're going to converge or not, definitely has its own challenges. I haven't tried it.
Okay, thank you so much.
Yeah, one more question.
So this is Gugan here. Thanks for your talk. So your optimal policy is time dependent here. So is it obvious that as t becomes infinity, the tth component becomes closer and closer to the optimal risk neutral policy? That is the first question. And the second question is, changing this time dependent optimal policies in practice and in to deal with in theory. I wanted to know, is it worth looking at the stationary analog and like finding the optimal policy within the class of stationary policies, and do you have any results which say how close the performance would be with this time dependent optimal policy? Thank you.
So if I understand your first question, you're talking about the connection between this and the risk neutral. So what I mentioned is when t grows, the value function becomes the risk neutral, becomes closer and closer to the risk neutral value function. But if your question is, if I solve a risk neutral MDP and see how well it optimizes the ERM, then I think depends on the problem, and probably it's not going to work very well.
No, that
right?
was not
because
my question.
It completely ignores.
No, my question was.
I didn't get it then.
Yeah, you have this time-dependent optimal policy, right? So pi t star. So your
Correct.
optimal policy has this component at time t. So I wanted to know, as your little t, right, becomes larger and larger, would that pi t star equal the optimal risk-neutral policy? So in the risk-neutral setting, you would have a stationary optimal policy, right? So as little t becomes larger and larger, would pi t star, start looking more and more like the optimal risk-neutral policy?
Oh, okay. Yeah, the policy when t grows, the policy becomes similar to the risk neutral policy.
Yes, that was my question.
But not at the earliest stages.
So I was wanting to know, is it worth? How challenging is looking at the time-dependent optimal policy in practice and theory, and is it worth looking at an analogous stationary optimal policy? Maybe that will be very different to the risk averse optimal policy.
So basically, your question is if we know that the true solution is in the time-dependent space, in the Markovian space. Basically, Markovian deterministic is the optimal solution. Now you are saying that if instead of searching in that space, we search for the stationary deterministic instead.
Yes.
How much we lose by doing that?
Yes.
This is, I think, what you propose.
Yes, that is the question. Yes.
Yeah, so I don't know. I don't have any bound for that. This is a good question. We can look at it, but I don't have any bound for this. I don't know how much you're going to lose.
Okay, Mohammed, this is Prashant again. The last question is, can I turn your formulation to find risk-taking policies with beta less than 0? Will the theory go through?
Sorry, can you say again? I couldn't hear you well. Sorry.
Can I turn your formulation to come up with a risk-seeking policy by choosing beta less than 0? Will the theory go through for ERMs?
Oh, risk. So basically, you are optimizing, again, in the simple case for mean plus variance.
Yeah, mean plus. So in the simple case, it's mean plus variance. So if I maximize, it's like risk-seeking. I may maximize variance. Now the question is,
yeah, I think that's going to give you I think this is going to give you a risk-seeking algorithm.
No, but in your theory with all the Bellman equations, beta less than 0 is okay, is it? That's the question.
That's a good question. I don't know. I need to go through them and see whether that causes problem or not. Because everything that we have written it with beta positive.
Yeah, is there like an implicit assumption? Yeah, is there an implicit assumption that requires beta greater than 0? Or can I just use the same algorithms with a negative beta? That's the broad question. Yeah.
Yeah, that's the part that I'm just trying to remember the derivation and see if any place we. But what if we just go for minimizing ERM there?
No, the thing is, the point is like I want to go for a mean plus variance thing. Like for example, if you take stock market, I want to trade so that I have high volatility, high risk, high gain kind of thing. So I'll take a risk measure and try to maximize. Like if you take the exponential formulation of Borker also, right? I mean, it is like mean plus some constant times variance. So if I maximize it, I'm getting a risk-seeking policy there. So that's the parallel. That's the parallel I'm hinting at. You have an exponential that brings in the risk part. Yeah.
I don't remember any step that causes problem here, but to give you an exact answer, I need to look at the derivations. But I don't remember any place that we needed really the positivity there.
Yeah, that's the curiosity. Maybe I'll ping you offline. I mean, you can let me know offline by email or something. I'll be happy to know that.
And get back to you. Yeah.
The last thing is, what about RL extensions? Is there a way to approximately solve these Bellman equations?
That's actually one of the questions that was asked. As I mentioned, for the undiscounted case, I think in the Borkar main paper, they proposed something. I'm not 100% sure, but I think they proposed a model-free algorithm, if I'm not mistaken. So potentially we can, by replacing all the distribution with sampling, but coming up with guarantee, I don't know. Definitely requires some work. We haven't done it.
Yeah, this probably ties to Gohan questions about trying to find a stationary policy that may be doable. How bad it is, it's not clear. Yeah.
Yeah, my guess is going to the stationary. This is also another question that was asked. I think potentially in the general case, you're going to lose if you go to the stationary space. And but whether by how much, I don't know. But I can imagine that the loss might be big.
Okay, I think we are running out of time. I'll end my questions here and hand it to Professor
Thanks,
Bhatnagar.
thanks, Mohammed, for a wonderful talk. Let's thank Mohammed. All right, so we have a formal inaugural. Sorry for the delay. I mean, when Professor Vinod had come early in the morning, there was no one. So we requested him to come back again for formally inaugurating this workshop and to give you a brief talk, a discussion about CSA and the opportunities and so on. So Professor Vinod Ganapatiya was chair of the department.
So good morning, everyone. I realize I'm the villain that's standing between you and your morning coffee, so I'll keep it short. My slides. So officially, welcome to the RL workshop. You've already heard the first talk. So what I'd like to do is to give a brief word of thanks to the Walmart Labs Center for Technological Excellence in Algorithms and Learning, which was established last year, April 2024. That's actually financially sponsoring this workshop. And this workshop is in fact part of the activities that of the center. So the mission of this center, which was generously funded by Walmart for a 5-year period, is to elevate our research capabilities in foundational research with translational impact, training high-quality PhD students, postdocs, and pre-docs, outreach workshops such as this and summer schools, and international collaborations. So it's a large project. It's a 5-year-long project, and we are hoping for a lot of exciting work to come out of it. So many thanks to Walmart for this. Just a glimpse of the activities that have happened over the last year. It's funded a number of our PhD students via fellowships. We have Walmart postdoctoral fellowships as well. Many postdocs have joined the department in this way. Walmart pre-docs, about which I will have to say a little bit more later on in the presentation, and a number of workshops over the past year. So for those of you that are students, you might want to just take a look at the sampling of workshops here that were just held over the past year, and many more are going to be held over the next few years of this sort. So art and computing was held around this time last year, and of course the first iteration of this same workshop. There was a workshop on geometric algorithms in August 2024, workshop on computing systems in November, and 2 schools on theoretical computer science, including one that attracted the leading lights of computational geometry just last month. So with that, let me just tell you briefly about our department, the CSA department. This is a very uniquely named department. Unlike other computer science or computer science and engineering departments, we are computer science and automation, which is also conveniently stands for computer science and AI, which is what people want to hear these days. So you can interpret in any way you want to. But our department is 55 years old at this point. It was founded in 1969 by Professor B.L. Dikshitalu, and the founding chair was Professor I.G. Sharma. We had our golden jubilee in 2019, and by several metrics, for example, csrankings.org, which essentially measures research output, our department is the only Indian CS department that ranks in the top 100 worldwide. This is for the 10-year period from 2014 to 2024. And our faculty have presence in all international fora, such as top journals, top conferences, and so on. And our graduates are highly sought after nationally and internationally. In CSA, we have research projects that broadly span these three spectrums, these three topics, and of course a spectrum of topics that sort of cover interdisciplinary topics as well. So computer systems, AI, ML, and theory. And what I've listed here on this slide are just a sampling of research projects going on in this department, in our department. This is by no means comprehensive. So just to show you a variety of work that's going on. As I mentioned, our department has a routine presence at all of the top venues in CS. It's no longer, a surprise to publish here, but one of the unique honors that our department has is that in many cases, our department faculty were among the first from India to publish at many of these leading venues. So it's a point of pride for us. Our students, of course, we can't do any of this without them. All of them are extremely accomplished and have been winning several awards, including prestigious fellowships, as well as things like the ACM. They do very well at the ACM India Doctoral Dissertation Award competition, either winning the award outright or winning the honorable mention. Many of them go on to pursue graduate study, PhD, and masters at all of these places that you see listed on the slide at leading universities worldwide. So just a sampling of some student recognition received last year, including things like Google PhD fellowships, the Kotak IISc PhD fellowship, and this is just a sampling of student honors received over the past year. Of course, I like to boast about my colleagues as well, and many of my colleagues have gone on to win really prestigious prizes in their disciplines. Notably, the ACM India Early Career Award, which was started in 2020, we are happy to say there is a hat-trick of awardees from the CSA department, including most recently this year my colleague Professor Arka Prabha Basu, who just, it was announced last week that he's received the award for 2024. And of course, many congratulations to Professor Shalabh Bhatnagar, who was elevated to the rank of IEEE Fellow this month, effective this month onwards. For those of you in the audience that are interested in AI-related activities, I'd also like to mention a new initiative in CSA. This was just funded and the project got started last month. It was funded by ETM Systems. It's a new lab for equitable AI. It's going to be housed within the CSA department, which is going to consider topics such as fairness, accountability, and so on. And so this project is being led by around 5 faculty within computer science and automation. So please expect some workshops and tutorials and so on that will be associated with this center in the near future. And let me close with some opportunities for students within the CSA department. For those of you that are students, of course, you are familiar with the PhD and master's programs here at IISc, but let me also put in a brief word for this program called Spark. It's not really a program. I should probably call it an initiative, which is a pre-doc initiative that was started by our department. SPARKS actually stands for Students Performing Advanced Research in Computer Science, K for computer, right? So the cycle for SPARKS pre-docs is opening shortly, and we'll be accepting applications over the next 1 month or so. So for those of you that are finishing or close to or have just recently finished your BTechs or master's degrees, and are thinking about research but are not entirely sure about a PhD degree, for example, this is your chance to spend a year doing research in close association with a faculty member in CSA and see if it's really your thing, right? So this program was specifically tailored for that. So you will be working with a faculty member as a research assistant. There is a stipend or an honorarium associated with it. So kindly apply. The number of seats is very limited, around 10 or so, but if you get selected, it will give you exposure to research. And finally, many thanks to our organizers, Professor Guhan, Professor Shalab, as well as our staff, Kushal, Akshaynath, and Sanjay, for making all of this possible, and wishing you a fruitful time at the workshop.
Right, so thanks a lot, Professor Vinod. As a token of appreciation. Yeah, thanks for taking the time out, and we'll break for coffee, and we'll reassemble at 10:45. Yeah.
Okay.
Okay, welcome to the second talk on day 2. So we have Professor Aritra Mitra who will be talking about finite time theory of robust RL, and Aritra Mitra is currently an assistant professor in Department of ECE at NCSU. Previously, he was a postdoc at UPenn from 2020 to 2022, and he received his PhD from Purdue, MTech from IIT Kanpur, and his bachelor's degree from Jadavpur University in 2013, all in electrical engineering. He was a recipient of the University Gold Medal at Jadavpur and the Academic Excellence Award at IIT Kanpur. His research interests are in obviously in reinforcement learning, but also control theory, statistical signal processing, broadly ML, and distributed algorithms. I will look forward to a great talk. Thanks.
Thank you so much for that kind introduction, and thank you to the organizers for inviting me to this workshop. It's really a great pleasure and honor for me to be speaking in front of this audience. Okay, so what I plan to do today is go over some recent results that are focused on two main themes. The first theme is going to be centered around the topic of finite time analysis of certain class of reinforcement learning algorithms. And in the second part of the talk, I'll turn to the question of robustness, where the information that's received by the agent is imperfect. Okay, so typically you sort of assume that the information returned by the world is perfect, it's consistent, but we'll look at a departure from that standard paradigm. Okay, and these ideas will become clearer as the talk progresses. So let's get started. We'll start by looking at what a standard reinforcement learning setting looks like. So you typically have an agent that's interacting with an unknown world. To know the world better, the agent pokes the world by taking some actions. The world responds by providing some feedback in the form of rewards. And using these rewards, the agent gains a better understanding of the world that it's interacting with. And this allows the agent to take better actions over time. Okay, so what do I mean by better? The idea here is to play a sequence of actions that maximizes some kind of long-term cumulative reward. Okay, and this will be made precise in a later slide. Okay, and why is this a learning problem? It's a learning problem because this environment is not known to the agent a priori. Okay, so this creates some uncertainty in the problem to begin with. So this is the standard RL pipeline, and it's found a lot of success across several applications. If you're thinking about like big games or robotics, it's shown a lot of empirical promise. But if you think about many of these contemporary applications, you need to contend with high dimensional data, and you have several actions and states to contend with. Okay, and as a result, it's observed in practice that in order to train an algorithm to a desired level of accuracy, one often needs a large amount of data. Okay? So a natural question that one can ask here is, how many data samples do we need to achieve a prescribed level of performance? And this in turn requires understanding these algorithms more finely. We need a non-asymptotic finite time analysis of these algorithms. Okay, so this is going to be the motivation for the first part of the talk. The second part of the talk will concern the topic of robustness. This is broadly motivated by the recent surge of interest in adversarial machine learning, where the idea is to think about robustness of machine learning algorithms to perturbations in the input data set. Okay, this is a very popular sort of topic of research, but most of the work in this space looks at supervised learning problems, such as classification. Okay, but if we ask similar questions for data-driven decision-making problems, there is much less that we understand, especially when it comes to principled theoretical guarantees. Okay, so with this in mind, we are going to revisit the standard ML sort of RL paradigm. And in the standard setting, one assumes that the data that's received by the agent from the world is always consistent with the world. Okay, so there is never any deviation. You receive perfect feedback. In contrast, we are going to think about a scenario where there's an adversary sitting between the environment and the agent, and will allow this adversary to perturb a portion of the data arbitrarily that's seen by the agent. Okay, and in this RL context, the data is the rewards seen by the agent. So this raises the question that the existing RL algorithms that we use right now, are they robust to this kind of a model, attack model? And if not, how can we robustify these algorithms to adversarially perturbed rewards? Okay, so this is going to be fairly recent work. So with this in mind, here is the outline for the talk. The two themes that that I mentioned before are going to be united by the fact that we'll be thinking about a common problem. Okay, so we'll be thinking about these problems in the context of policy evaluation with the temporal difference learning algorithm. In the first part of the talk, I'll provide a new simple finite time analysis for this algorithm, and we'll mention an application of this proof technique to handling delays, time-varying delays in the system. In the second part of the talk, I'll introduce the reward corruption attack model. I'll show that the basic TD0 algorithm is vulnerable to this attack model. This can be shown provably. And this will motivate the design of a new robust TD algorithm. So I'll walk you through the main ideas behind the algorithm. I'll talk about some performance guarantees, and I'll also characterize information theoretic fundamental limits for the setting. Okay. So then let's get started with the first part of the talk, where I'll discuss this new proof technique for TD learning. And this is based on a paper in the IEEE Transactions on Automatic Control from last year. Okay, so let me start by setting up the necessary technical background. We're going to be thinking about a Markov decision process with finite states and actions. I'm going to use S to denote the state space, A to denote the set of actions. P is going to represent a set of action indexed probability transition kernels. R is going to represent reward functions, a set of reward functions, and gamma is going to be the discount factor. Okay, so let's go over each of these objects one by one. We'll use RSA to represent the immediate expected reward seen by the learner when it's in state S and when it plays action A. We'll use PS prime SA to represent the probability of transitioning to a new state S prime, given that currently we are in state S and we play action A. And for this talk, we are going to focus on deterministic policies which map states to actions. And if we fix the policy, then it's going to induce a Markov reward process that's characterized by a reward function that I'll denote by R sub pi and a transition matrix that I'll denote by P sub pi. Okay, so how do we get R sub pi? You go to RSA and you just replace A with pi of S. And that will give you R pi of S. And in a very similar manner, you can construct P pi from this object. So then, to determine the goodness or the quality of a policy, we are going to introduce this notion of a value function, V pi. And V pi of S is going to be defined as the expected infinite horizon discounted sum of rewards, given that we start from the initial state S and we keep playing the policy pi forever. So with this background, the central goal in reinforcement learning is to find a policy that maximizes V pi without prior knowledge of the transition kernels and the reward functions. In this talk, however, we are going to look at a much simpler problem where, given a policy pi, our goal is to just evaluate the value function V pi corresponding to this policy. And this is known as the policy evaluation problem. Now, the first thing to note here is that V pi is the fixed point of a policy-specific Bellman operator that we'll denote by tau pi, where tau pi takes the following form. Okay, so how do I get tau pi? You just go back to the previous slide, and the expectation that I showed you, it can be broken up into the immediate reward and the expected reward to go. Okay, so if you decompose it in that manner, you will immediately get this equation. So based on this fixed point property, we can easily set up a recursive algorithm to evaluate V pi. You'd just start out from any initial guess, and you'd keep applying the operator tau pi repeatedly. And given the fact that this operator is strictly contractive in the infinity norm, it's very easy to show that the iterates generated by this algorithm will converge exponentially fast to this object V pi. But notice that in order to apply this algorithm, we need to know this operator tau pi, which in turn requires knowledge of the transition probabilities and the reward functions of the MDP. Okay, so the question that we want to ask here is, what do we do when the MDP is unknown? So to address this question, Richard Sutton introduced a family of algorithms known as the temporal difference learning algorithms back in 1988. What we'll look at are variants of these algorithms for MDPs where you have several states and actions. And this requires some kind of function approximation. So we'll be looking at the simplest form of function approximation known as linear function approximation, where the goal is to find a parametric approximation, V hat theta, of V pi, which lives in the column space of a predefined matrix, feature matrix phi. Okay, so this matrix is just given to us ahead of time. So if we denote the columns of this matrix by phi1 to phi k, we are trying to find the projection of V pi onto the column space of these vectors. And so mathematically, you can write down v hat theta as a linear combination of these columns, and the weights that we assign to these columns form the feature vector theta that we're going to update over time. And the thing to note here is that the number of columns k is typically much lesser than the number of states, meaning that this parameter theta that we'll update lives in a low dimensional space. Okay? Now, if we focus on a particular row of this vector, let's think about the row corresponding to state S, then the approximation for that state, which we'll denote by v hat theta S, can be written down as the inner product between the sth row of this matrix, which we'll call phi of S, and the vector theta. And this phi of S, we'll call it the feature vector for state S. So with this background, I can introduce the simplest of the TD learning algorithms, known as the TD0 algorithm with linear function approximation. Okay, so this algorithm is going to operate in discrete time steps. At each time step, we'll play the policy pi to be evaluated. And upon playing the policy pi, we'll observe a data tuple that comprises the current state st, the next state st plus 1, and the current reward at state st under the policy pi. Okay, so r pi st. Using this data tuple, the agent is going to create what we'll call a TD0 update direction. And once the direction is constructed, it will just update the parameter by taking a small move along this direction with step size alpha. Okay? So what is this direction? Let's take a closer look at it. The first thing to note here is that you can think of this object as an estimate, a bootstrapped estimate of the reward to go from the new state st plus 1. So if you add that to your current immediate reward, this gives you an estimate of the value function from the current state st. And what we are subtracting off from it is our previous guess of the same object prior to observing the data xt. Okay, so you can think of this difference as the innovation that we observe once we get to see xt. And what we are doing is we are taking this innovation signal and scaling it with the innovation gain, which is the step size, to update the parameter. Okay, so if you have seen like a Leuenberger observer for estimating the state in an LTI system, this is very similar in spirit, because you take the measurement innovation there and multiply it with the Leuenberger gain. Okay, so this is very similar. So what makes this algorithm non-trivial to analyze is the fact that there is randomness in this algorithm from the parameter theta, which in turn gets its randomness, inherits its randomness from this data tuple xt. And the thing that makes it challenging is the fact that these xt's are not IID over time. Okay? So they're all part of one single Markovian trajectory, and as such, these data tuples are correlated over time. Okay, and this is what's going to make the analysis complicated, as we'll see in a few slides. So before we go into the technical details, let's take a look at what's known about this algorithm. So in the seminal paper in '97, John Sissiklis and Benjamin Van Roy provided an asymptotic analysis of TD learning algorithms with linear function approximation. And their results are asymptotic in the sense that they'll tell you something about the convergence of these algorithms in the limit of infinite samples. Okay, but although these ideas provide foundational insights, they don't immediately give you rates of convergence. And obtaining such rates of convergence turns out to be quite non-trivial. So this is a quote from their paper, where they say that though temporal difference learning is simple and elegant, a rigorous analysis of its behavior requires significant sophistication. So they could probably look into time, because it took nearly 20 years to come up with the first non-asymptotic analysis of TD algorithms under Markov noise. And this analysis is first provided by Bhandari, Russo, and Singhal in their 2018 paper. And they performed this analysis by making interesting connections to the dynamics of stochastic gradient descent. But if you look closely at their proof, you'll notice that there's a projection step in the algorithm to ensure that the iterates generated by the algorithm are uniformly bounded. Okay? And this considerably simplifies the proof. Now, in a follow-up paper by Shrikant and Ying, they were able to get rid of this projection step, but this came at the expense of a more involved proof. So the question that we want to ask here is there an alternative way of analyzing these algorithms, which is simple, like in the Bhandari paper, but one that does not require a projection step? So to see why this is an interesting question, let's go back to the TD update direction. Okay? one can easily sort of see that this update direction is affine in the parameter theta, where all the randomness that comes from Markov sampling is contained in this time-varying matrix AT and this time-varying vector BT. Okay? So now let's make the standard assumption that the underlying Markov chain is aperiodic and irreducible. One can then show that this time-varying matrix AT is going to approach a stationary matrix A bar in expectation, and similarly BT is going to approach a stationary vector B bar. So now using A bar and B bar, we can construct a steady state version of this TD update direction. Okay, so you can think of this as what the TD direction will look like once enough time has elapsed. So with this insight, we can write down the right-hand side of the TD recursion by splitting it into two parts. The first part is the steady state or the nominal behavior of the algorithm, which is governed by G bar. And the second part, you can think of this as a disturbance term that captures the distance to stationarity. Okay? Now at this stage, it is tempting to think that if AT eventually approaches A bar and BT eventually approaches B bar, then GT should also eventually approach G bar. Okay, so you'd think that this is a small term, so that if this steady state dynamics is well behaved, it's stable, you'd have like a small additive disturbance hitting this dynamics. And by using something like an input to state stability kind of an argument, you'll be able to argue that the overall dynamics is also well behaved. Okay? But where this idea breaks down comes from the fact that this disturbance term depends on the current iterate theta t. Okay? So even if AT is close to A bar and BT is close to B bar, it could still be that this term is large because the theta t inside it could be large in magnitude. Okay, so at this stage, a projection step can really help you, because as soon as you project, the magnitude of theta becomes, it can be uniformly bounded. It lives inside a compact set. So then this disturbance term will indeed become a uniformly bounded perturbation. Okay, but recall that we don't want to project. Okay, so this is what's going to make the analysis tricky. So to see what we do, let's first look at the non-noisy version of the algorithm. So let's think about the steady state version of the algorithm. If we think about the steady state update direction and we equate it to 0 to find the fixed point of this steady state direction, we'll obtain the best fit parameter theta star, which happens to be the solution to a projected Bellman equation. Okay, so this is the optimal point that we want to converge to. Now let's fix a particular theta and think about the vector that connects theta to theta star. It turns out that this vector is going to make an acute angle with the steady state update direction G bar theta. Okay, so what this means is that if, at least in the steady state, we move along G bar theta, it's going to bring us closer to our point of interest theta star. Okay? And this geometric observation can be formalized. You can show that the inner product between this vector theta star minus theta and G bar theta is lower bounded by the squared Euclidean distance between theta and theta star. Okay, and mu here is just some problem dependent parameter. Okay, and I should mention here that this is not a new result. This in fact goes back to the work of Tsitsiklis and Roy. The second fact that can be easily proven comes from the observation that this noisy TD update direction and the steady state are both affine in the parameter. So using this, you can show that both of these directions are two Lipschitz. Okay, and the two here comes from the assumption that the features are normalized. So these are the two facts that we'll exploit in our analysis. Our analysis is going to comprise of three main steps. In the first step, our goal will be to create a basic or crude recursion for the mean square error. And I'm going to represent the mean square error at time t by dt. So just using the two facts that I showed you in the previous slide and one or two lines of algebra, you can arrive at this recursion, which comprises of three terms on the right-hand side. The first term is a contractive term that comes from the steady state dynamics. The second term is a noise variance term, which is on the order of alpha squared, which is typical of noisy iterative algorithms. And the most interesting term is this term, which comes from Markovian sampling. Okay, so it captures the gap between the noisy TD direction GT and its steady state version G bar. Notably, if we had sampled the data from the stationary distribution in an IID manner, this term would vanish, And the recursion that you'd be left with would mimic the kind of recursion you get when you analyze SGD. Okay, so it would be a very standard recursion to analyze. So really, the work comes down to controlling this term. Okay. So in the second step of our analysis, we'll establish the key result that is needed to control the Markovian bias. Yes. Yes.
Can you just quickly motivate why the second term, the O of alpha square sigma square, does not depend on theta t?
Right, so I've decoupled the effect of theta and sigma. So this sigma has nothing to do with theta t. This sigma is just coming from a norm bound on GT. And if you recall, GT is AT theta minus BT. So what I do is basically split up that object into AT theta minus theta star. You'll get like a theta star plus BT kind of a term. BT contains the rewards which are uniformly bounded. AT contains the features which are uniformly bounded. So that term essentially captures the sigma effect.
That doesn't still explain why there is no norm theta squared here.
There is a, no, so I mean the norm theta square is contained inside dt. So if you look at dt, there is a norm theta square theta t inside it. So all those terms have grouped over here. And there will be some other theta t minus theta star kind of terms that emerge from this, which I've left it as inside this term for now. Okay, but the other terms that contain theta t minus theta star I've grouped inside this term.
But there will be like a alpha square theta t minus theta star term as well, right? But
that will come later from the analysis. So from this, I'll be able to manufacture an alpha squared theta t minus theta squared term later on in the analysis. Yes, it will come from this term. Yes. Okay. So what we can show is that there exists a constant step size alpha which scales inversely with the mixing time, such that if you pick the step size of this form, then the iterates generated by this algorithm, okay, will be uniformly bounded in the mean square sense on their own. Okay, so I don't need to project to make this happen. This is just a property of the algorithm. Okay, so that's the key message. Of course, this requires that you know the mixing time, tau mix. And the key idea behind this proof will be a careful inductive argument. I'll sketch out the ideas behind this inductive argument in a moment. But before we get there, let's see how we can put this result into use. Okay? So what we can immediately show as a consequence of the previous result is the fact that the Markovian bias term is also going to be uniformly bounded by this object over here. Okay, so it's going to be order alpha tau mix times b, where b is this object, which contains the effect of sigma squared and the initial error. So now that we have this, all we need to do is go back to the recursion from the first step, the crude recursion, and replace the time varying Markovian bias term with the uniform bound on it from the previous slide. And as soon as we do that, we get a much simpler recursion where instead of a time varying iterate dependent disturbance, you now have a uniformly bounded disturbance which is on the order of alpha squared. Okay, so this is exactly the kind of recursion now that you get with SGD. And once we arrive at this, the proof is really straightforward. You can see that if you maintain a constant step size, you'll get exponential convergence to a noise ball. And if you want to get exact convergence, you can pick a step size that scales inversely with capital T, and you'll get the standard O1 over T kind of rate. Okay? So what are the three main steps in our analysis? The first step is to just use basic properties to write down a recursion for the mean square error. The second step is going to be to use induction to argue uniform boundedness of iterates. And the third step is to use the uniform bound on the Markovian bias to refine the bound from the first step by replacing the time varying perturbation with a uniformly bounded perturbation. Okay, and as we'll see, these three steps are going to constitute a general recipe that we can use to analyze recursions that are more complex than the basic TD0 recursion. Okay, but before we do that, this is really at the heart of our analysis. So I want to spend a few more slides talking about what we do here. So remember that our goal is to argue that the iterates remain uniformly bounded. Okay? The way we are going to analyze this is by splitting up the time axis into two parts. Time steps that are before the mixing time tau mix and time steps that are greater than tau mix. Now for time steps that are lesser than tau mix, we can show that if the step size scales inversely with the mixing time, the iterates will remain uniformly bounded deterministically. Okay, so this will happen deterministically. The way to do that is very easy. You just unroll the TD recursion and you use the following easily proven bound on the norm of the TD update direction. Okay? And this lemma is going to serve as the base case of our induction proof. So this gives me boundedness of iterates for all time steps up to tau mix. Our next goal is to arrive at a similar bound for time steps that are greater than tau mix. So the next result that we'll prove in this context is to fix a time step that is now greater than tau mix. And here notice that I'll make this assumption in the statement of the lemma, that the mean square error is bounded for all time steps up to time step t. Okay, so this will greatly simplify the analysis. You'll see why I do this in a moment. If we make this assumption, then we can show that the change in the iterate between t minus tau mix and t is again uniformly bounded in the mean square sense. Okay? This is also a very easy proof. You just write down the total change as a sum of incremental changes across continuous time steps. We observe that each change over here is caused by the TD update direction. We use the norm bound on the TD update direction from the previous slide, and then we just plug in this object. Okay, so we use this to complete the proof. So the main point is that this assumption is helping us in the proof. Okay. So then in the final step, what we'll do is we'll again pick a time step that's greater than tau mix. We're again going to assume that this is true for the time being. And once we do that, we can argue that the Markovian bias term is going to be of, again, uniformly bounded of this order. Okay, so the way to do this is to condition into the past sufficiently to exploit the geometric mixing property of the underlying Markov chain. And then we can use lemma 2 from the previous slide in conjunction with this assumption. Okay? But once we sort of prove lemma 3, now we're almost done in terms of the inductive argument. We'll assume that dk is upper bounded by b for all time steps up to time step t. And as a part of our induction hypothesis then, we can apply lemmas 2 and 3, right? Because this is what goes inside the statement of the lemma. So as soon as we use this in our induction hypothesis, we get this bound. So we can then plug in this bound into the crude recursion from step 1. And with one line of algebra, you'll be able to show that dt plus 1 will also be upper bounded by the same b. So then effectively what we end up showing is that all the dt's will be upper bounded by b, meaning that the conditions that we needed for lemmas 2 and 3 to hold will now always hold. Which means that this uniform bound on the Markovian bias will also always hold. Okay, so we are doing a two-step argument where in our first step we have a very modest goal. We just want to argue uniform boundedness of iterates in an inductive manner. As soon as we get that, we can use the same results to get a finer recursion to prove the rate. Okay, so hopefully this gives you some insights into what goes on inside the inductive proof. Now let me tell you one particular application of these ideas where we wanted to study the effect of time-varying delays in the context of stochastic approximation algorithms. So you can think again of the TD update rule. And this time, instead of making moves along the true TD update direction, we're going to make moves along a delayed version of the direction, where the delay comes from the fact that we're evaluating the TD update direction not at the current iterate theta t, but at a stale iterate theta t minus tau t. Okay, and tau t here is the delay incurred at time t. This delay can be random, it can be time varying. All we'll assume is that the delays are uniformly upper bounded by tau max, okay, some object tau max. And the motivation for looking at this comes from networked settings where information gets exchanged over imperfect channels which can be lossy, noisy, which can drop packets. So there is a lot of work that's looked at optimization with delays under IID noise. But if you look at these papers, majority of them assume constant delays to simplify the analysis. And the few papers that look at time varying delays need to construct non-trivial, non-intuitive Lyapunov functions to complete the proof. Okay, but as far as we are aware, there was no prior analysis of stochastic approximation algorithms of this form, at least in the finite time regime, with time varying delays under Markov noise. Okay, so this is the gap that we wanted to address. But very quickly, this becomes messy. And the reason is as follows. When you want to usually analyze these algorithms, you're trying to write down a recursion involving the error at time t, and you want to relate it to the error at time t minus 1. Right? But in this case, because of the delays, your error at time t is going to depend on a bunch of terms from the past. Each of those terms are going to depend on further terms from the past, and so on and so forth. Okay, so if you try to write down a mean square error recursion like we did before, you will get the 3 terms that we got before, but now you end up with a bunch of delay terms from the past, each of which further depend on other delay terms from the past. Okay, so this is a messy recursion. We were stuck here for quite some time, and this is the bottleneck which actually motivated the simpler proof in the first slides, the first few slides that I showed you. Because once you have that proof in mind, one natural way to address this problem is to think about both of these terms as a collective disturbance. You can lump them together. And you can try to use the same idea where you first use induction to argue uniform boundedness of iterates. And once you have that, you can replace this iterate-dependent, time-dependent term with a uniform bound on it. Okay, so it turns out that these details do work out for this setting. And the kind of result that we can prove here is the following. Let's suppose that tau bar is the larger of the mixing time and the largest delay that you can see, tau max. What we can show is that if you pick a step size that scales inversely with tau bar, then you will again get exponential convergence to a noise ball. And this time, the exponent of convergence is going to get attenuated by this tau bar. Okay? So one interesting observation here is that if the underlying Markov chain mixes slowly, then you can tolerate larger delays. Okay, so if you're interested in more details, they're available in this IISc's paper from last year. But again, the main point here is that you can use this inductive proof technique to think about robustness to these kinds of perturbations induced by delays. Okay, so let me quickly summarize the first part of the talk. We developed this novel inductive proof. It's really short, so it's just about a page. The proof also extends to other TD lambda methods. You can use it to analyze more general contractive nonlinear stochastic approximation schemes. Okay, so these details are available in the paper. And we can also extend them to handle disturbances that are due to time varying delays. And you can also sort of think about other kinds of communication induced distortions where you, let's say, compress the update direction. Okay, so before I move into the second part of the talk, let me quickly position this line of work by relating it to the broader spectrum of research in this area, which can be grouped into 2 categories. You can think about asymptotic analysis, where there's a lot of rich work. You can also think about the more recent surge of interest in finite time algorithms. Within this space, again, you can sort of break it up into IID sampling regimes and Markovian sampling. With IID sampling, you're looking at scenarios where you make the simplifying assumption that data is sort of sampled in an IID manner from the stationary distribution of some Markov chain that's induced by a suitable behavior policy. Okay, and our interest is in the Markovian sampling region, sort of regime. And all we are doing is it's a small effort towards understanding this regime better. Okay? And I should mention here that this recent paper by Patil et al. Also consider Markovian sampling. They also don't require a projection step in their algorithm when it comes to mean square error bounds, but they look at a slightly different setting where they tail average the iterates. In contrast, we are looking at the last iterate from our algorithm and trying to get a guarantee on the last iterate. Okay, so that concludes the first part of the talk. Before I move into the second part of the talk, are there any questions?
Okay, so one thing is why is tail averaging bad compared to last iterate?
No. So, sure. I mean, we are not saying it's bad.
The second thing is I had a universal step size in that work.
Right.
Whereas you require eigenvalue information.
That's correct.
Yeah.
That's correct. So this is again not to say that tail averaging is bad. This is just saying that for the setting, let's say that's been studied by Bhandari and Shrikant, where you look at the last iterate, is there a way of analyzing it? And I can ask the question that, can your tail averaging proof look at other kinds of disturbances, right? It's not clear.
Okay, so the second question is, why is my proof not so simple compared to yours?
Right. No, so I don't claim that your proof is complicated. We are just saying that there is an inductive way to analyze and get rates for the last iterate, which can also be extended to other kinds of disturbances, right? And it's unclear whether other proofs can handle that.
Yeah, that part is not clear, but particularly for a linear system, at least trying to get, the question now is like, a related question is, can you make your step size universal with this so-called so-called simple proof, simply because we totally use the
Right.
linear system solution to manufacture the universality of the step size.
That's
Not
a great-
entirely sure it will extend to other schemes. Yeah.
No, that's a great question. And in fact, one of the reviewers asked this question. If you look at the Shrikant and Ying paper, it also requires the step size to scale inversely with the mixing time.
Not
and
just mixing time, it also requires the
eigenvalues, yeah. So I guess one thing you could do is, for the mixing time, you could look at data to construct an empirical estimate of the mixing time. But the analysis will be much trickier, right? Because the step size will depend on data now. So the step size itself will become random. And one could potentially use ideas from adaptive algorithms where the step size is random to analyze it. But that's about the best answer that I have.
Not the mixing time, I'm talking about the eigenvalue dependence.
That I don't know. So I can't. I don't have an answer for that. If the features are, if you assume that you're in a tabular setting, then that omega will essentially be the smallest entry of your stationary distribution, right? So you can kind of still estimate that from data, but other than that, I don't have a good answer to that question. Yes.
Okay, I'm done with my questions.
Okay.
Thanks.
Okay. Okay, so let me then move into the second part of the talk, which will be centered around the topic of robustness of reinforcement learning algorithms to perturbations in the reward sequences that are induced by an adversary. Okay, and we'll again be thinking about this problem in the context of policy evaluation, but many of the ideas that we'll talk about can also be extended to control problems using Q-learning. Okay, and this work is based on a paper that just got accepted to IISc, but it's not an archive. So if you want some preliminary version of it, we have some results in last year's CDC, but this is for a simpler tabular setting. Okay. So what I want to do here is at least set up the model, talk about the main algorithmic ideas, and then give you a flavor of the results. So recall again that our goal is to evaluate a value function v pi corresponding to a policy, value function v pi corresponding to a policy pi. We are now going to look at a generalization of the reward model from part 1 of the talk. With each state S, we are now going to associate a conditional distribution denoted by d pi of S, okay, such that whenever we are in state S and we play action pi of S, we are now going to observe a noisy reward that's drawn from this distribution. Because the main departure is that the rewards are no longer deterministic, they are noisy random variables. Now, what do we know about the statistics of these random variables? We know that they're unbiased. Okay, so if you take the expectation of Rs, you get back R pi of S, which is the true mean reward at state S under policy pi. And we'll make the standard assumption that these mean rewards are at least uniformly bounded by some object R bar. We'll also assume that the reward random variables have bounded variance. Okay, and the variance bound is going to be denoted by rho square. Okay, so the thing to note here is that we don't assume the noisy rewards to be light-tailed or sub-Gaussian. Okay, we don't assume anything other than the existence of the second moment. So these reward distributions could be heavy-tailed.
You're assuming the rewards are bounded, right?
No, so the mean rewards are bounded. Okay, it's not the true reward sample. So the true reward sample, the noisy reward can have unbounded support. And if you don't assume this, then the value function is not well defined, right? I need at least this. Okay, so that was the basic reward model. Now let's see how these rewards can be corrupted. So at each time step t, the learner is going to observe a signal r tilde t that is generated as follows. We're going to toss a biased coin with probability of heads 1 minus epsilon, where epsilon is some number between 0 and half. And this coin tossing is independent of all prior randomness. Okay? If the coin lands heads, the learner is going to observe a reward sample drawn from the true reward distribution corresponding to the current state ST. If the coin lands tails, then the reward is generated from a completely arbitrary distribution, which is under the control of an adversary. Okay, so compactly we can write down the distribution of R tilde t in the following form. And the main message here is that at each time step t with probability epsilon, the reward seen by the agent can be completely arbitrary, and it's under the control of the attacker. And this model is directly inspired by the Huber contamination model from robust statistics. So we'll be calling it the Huber contaminated reward model. So under this reward model, we'll ask three main questions. The first question is, if we still continue to run the basic TD algorithm, what can we say about its convergence? The second is, can we still hope to get a reliable estimate of V pi despite these corruptions? And the third is, what are the fundamental limits imposed by this kind of an attack model? Okay, so before we get down to answering these questions, let's take a moment to think about some of the challenges associated with this problem. The first thing to note is that because the rewards are coming from a heavy tail distribution, even in the absence of corruption, you can have samples that are drawn from the tail. So this makes it particularly hard to distinguish between inliers or true samples drawn from the tail and outliers that are generated by the adversary. Okay? And the second challenge comes from the fact that the data, again, the rewards are correlated over time. This makes it tricky to adapt results from robust statistics where one typically assumes that the data is IID. So with these challenges in mind, we can start to answer the three questions that I'd raised. The first question is, let's suppose we run the basic TD0 algorithm, okay, with step size sequence alpha t. Okay, and let's again make the standard assumption that the underlying Markov chain is aperiodic and irreducible, and let's recall that theta star was the optimal point in the absence of corruption. What we can prove is that under a standard choice of step sizes, with probability 1, the iterates generated by TD0 can be made to converge to a new point now that I'll call theta tilde star, which turns out to be the convex combination of the true optimal point theta star and a new point C, which is a corruption vector that can be controlled by the adversary. Okay, and the main corollary here is that this point theta tilde star can be made to be any arbitrary point by choosing C appropriately. Okay, so this is a very simple result and it's perhaps unsurprising, but it conveys an important message, namely this basic TD0 algorithm is vulnerable in the face of this kind of an attack model. Okay, so this motivates the need for a new robust algorithm. So what I'll do next is sort of provide the high-level ideas behind the algorithm, and then we'll go into the technical details. Okay? So for simplicity, let's assume that our MDP is a grid of this form, and we are in a tabular setting where we can afford to maintain estimates for every state. So then let's zoom in on a particular state S. Okay? Now intuitively, if I'm a learner, I can maintain a history, a memory buffer, of all the rewards that I've seen each time I visited state S. So as I keep playing the policy more and more, I'll get to see more samples corresponding to state S. And under our reward model, the corrupted reward model, a majority of these samples are going to be uncorrupted with high probability. Okay, so this tells us that there is hope in terms of constructing a robust estimate of the mean reward corresponding to status. Okay, so but of course we still need to deal with temporal correlations. But let's suppose that this is manageable. Even if it's manageable, there is still a more interesting situation at play here. Since these estimates that we'll construct are based on noisy data, all guarantees that are associated with them will be probabilistic in nature. So we cannot rule out the possibility of rare events or extreme events where these estimates are incorrect. So we still need a way to control the error on these atypical events. Okay? So this leads to the second main idea, where we are going to construct a dynamic threshold. This threshold is going to keep track of the typical concentration interval within which our estimates will lie. So as soon as we see estimates that fall outside these intervals, we're going to threshold them. with the reasoning that these estimates are generated on a rare event. Okay? So the real key over here is to design this threshold in a careful manner so that we only threshold on rare events. Because if we threshold too often, we'll end up with vacuous bounds. So these are the two main ideas. Now let's try to formalize them. To do that, let's again go back to the TD update direction. And let's make an observation that the rewards only affect the term BT, but not the term AT. Okay? Now, under the assumption that the underlying Markov chain is aperiodic and irreducible, BT is eventually going to approach its stationary value, B bar, which is just the expected value of phi RS with respect to the stationary distribution mu. Okay? So if we can somehow maintain a robust estimate of B bar, then we are done. So let's think about some ways that we can do this. Now, motivated by the structure of B bar, one idea could be that for each state S, you maintain separate estimates of mu S and R pi S based on data. And then you can just plug in these estimates inside this kind of an object. Okay, so this is a reasonable thing to do, but unfortunately, it's going to completely defeat the purpose of function approximation, right? Because now you're going to be maintaining estimates for every state, which is something that we want to avoid when we're doing function approximation. On the other extreme, if you don't want to maintain separate estimates for every state, then you can just look at all the rewards that you have seen thus far without linking them to any state, and you can pass them through some kind of a robust mean estimator. If you do that, you will end up with an estimate of this scalar object, but there is unfortunately no way, at least no obvious way, of going from this scalar object to this vector B bar. Okay, so this tells us that we need to do something else. So here is what we do. Our idea is to maintain component by component estimates of B bar, and note that the dimension of B bar is much smaller than the number of states. The dimension of B bar corresponds to the number of features. Okay? So for estimating the ith component, we'll define an object yik, which is the product of the reward seen at time k times the ith component of the feature vector corresponding to the state at time k, phi of sk. And we can think of yik as the information corresponding to the ith component at the kth time step. So then standing at any given time step t, we'll collect all the yiks up to time t, and we'll pass them through what we'll call a robust mean estimator that can handle Markov data. And I'll explain what this estimator is in a moment. And this estimator is going to take as input the failure probability delta and also the mixing time of the underlying Markov chain. And it's going to provide as an output a reliable estimate of the ith component of B bar. Okay? The main intuition here is that if the underlying Markov chain is stationary, then each uncorrupted yik is going to provide us an unbiased estimate of the ith component of B bar. Because that's the fact that we leverage. Okay, so what is this robust estimator? It's a simple subsampled median of means. Okay, so we take the data set, we subsample it, where the subsampling gap depends on the mixing time of the underlying Markov chain. The reason we subsample it is to create a data set where the samples are roughly independent over time. And once we have the subsampled data set, we just apply a simple median of means. Okay, so we break up this data set into L buckets. We compute the mean inside each bucket, and we take the median of these means. Okay, so that gives us an estimate of the ith component of B hat t. So what we can prove, yes. No, please go ahead. It does depend on the policy that we are choosing. So the mixing time is the mixing time of the Markov chain induced by the policy that we're trying to evaluate. So we are sort of assuming that there is a priori knowledge of this mixing time, because this is sort of like an assumption that people have also used in this literature. But you're right that, I mean, if I don't know the underlying MDP, how do I know the mixing time of the Markov chain induced by the policy?
Yes, as long as you're evaluating, it's fine to use the, I guess, but.
This is an assumption that we need at the moment. I don't know of a way to get around it for the time being, but yes.
Sure, thank you.
Okay. Good question, yes. So what we can prove about this estimator is that if we choose the subsampling gap and the number of buckets appropriately, then we can establish the following guarantee on the ith component. Okay, and there are three main aspects to this bound. The first concerns the statistics of the reward distribution. So the bounds on the reward mean and variance show up over here. The corruption fraction is going to show up over here. And as you increase the number of samples, you'll get the typical square root 1 over t kind of rate, but this is inflated by the mixing time tau mix. Okay, and as far as we're aware, these are the first guarantees for robust mean estimation under Markovian data. So you can potentially. Sorry? Tau is going to be slightly larger than tau mix for the proof to go through. So it will be tau mix times some log factors. Okay. Yes. So tau is O tilde tau mix. So this gives us an estimate of b hat. But if you look at the bound on the previous slide, the guarantee that we have on b hat is probabilistic. So again, there will be rare events where these guarantees may not hold. And we need to ensure that even on these rare events, our error does not blow up. Okay, so the idea that we'll use here is to construct a dynamic threshold GT, which directly is informed by the bound on the previous slide, so it's not ad hoc. And as soon as we have this threshold, the idea is quite simple. We'll look at the guarantee from the robust mean estimation module. We'll look at the norm of that object. If it exceeds this threshold plus the effective noise variance, then we'll just reset it to 0. Okay? And the idea here is that this ball of radius gt plus sigma is where we expect this object b hat t to typically live inside. So if it falls outside this ball, then we'll sort of reason that this has happened due to an atypical event where it's okay to threshold. Okay, and it should not come as a surprise that this threshold needs to be designed carefully, because if we just unnecessarily threshold, then we'll get too many zeros and we'll get vacuous bounds. Okay, so let's put these two ideas together. We take the reward corruptions, we feed it into this estimator, and then to safeguard against rare events, we pass it through this dynamic threshold scheme. And once we get the final b hat t, we just go back to the TD update direction and replace bt with its robust counterpart, b hat t. So that gives us a new direction, and then we again make updates exactly like before. So let me quickly just tell you about the main results. What we show is that if the step size is chosen suitably, and if we run the algorithm for large enough time, then we can establish the following mean square error, which comprises of two parts. The first part is the standard O1 over t kind of rate that you get with basic TD0, but then you also have this additive term which captures the effect of corruption. Okay, and the thing to note here is that this epsilon gets amplified by the noise level and some problem dependent parameters, but it does not depend at all on the magnitudes of the attack vectors. It only depends on the corruption fraction, which is a number between 0 and half. Okay? Now if you set epsilon to 0, these results are going to match bounds, known bounds, up to a multiplicative OK factor, where k is the number of features. And if we set epsilon to be non-zero, then this additive corruption term is consistent with results that people have shown for stochastic multi-arm bandits with similar reward corruption models. Okay, so there is reason to believe that this is tight, but we'll formally show that this is tight by proving a lower bound. And for this, it suffices to consider a tabular setting where the learner observes IID samples. In the interest of time, what we can prove is that we can establish two different instances of our problem such that any estimator that you construct will incur an error of this order on at least one of the two instances. Okay? And this will happen with a constant probability, in this case with probability half. So if you square this error bound over here, you will get your mean square error, and we can see that the dependence on epsilon on 1 over 1 minus gamma squared and on the noise level rho squared are going to match the bounds on the upper, are going to match what I showed you in the upper bound. Okay, so these are tight. So let me not go into proof ideas. Let me just show you a plot where, if you just do a toy simulation with 100 states and 10 features, and you plot the mean square error, then even with a very small corruption fraction, the error can blow up with the vanilla TD algorithm. But complying with our theory, if you apply our algorithm, then you get error bounds that sort of settle down near 0, where this error floor is going to depend on the noise variance level. Okay, so let me just point to some quick open problems. We want to extend these ideas to more general stochastic approximation problems. We want to consider other kinds of attack models where, let's say, the states can be under attack, more refined lower bounds that capture the effect of Markovian sampling and function approximation. And finally, our algorithm requires knowledge of the mixing time, it requires knowledge of the bounds on the mean and variance, and it requires a ton of memory. Okay, so how can we get rid of all of this is an open question. Okay, so this is a big limitation of our algorithm. Okay, so let me stop here by showing you some of the relevant references, and I'll be happy to take questions. Thank you for your attention.
Sir, I have a question.
Yes.
So, did we cover both policy evaluation and optimization, or we covered only?
No, we only covered policy evaluation, but there is a CDC version of this paper where we cover the question of finding the optimal policy, but this is for a tabular setting, and it's for a synchronous sampling model where you get to access all the states at each time step.
Okay, so will we apply the same robustness techniques for optimization, or like will it be different?
Good question. We did use the affine structure of the TD update direction,
Okay.
which will not be the case when you look at, like, let's say, Q-learning with function approximation. So it's not clear a priori. I think so, but I mean, some details need to be worked out.
Sure. Thank you.
Yeah. But at least in the tabular setting, yes.
Yeah, I just have an empirical question. So if you use estimates of mixing time and whatever,
Yes.
empirically, how does the algorithm perform? Did you try?
I did not try it, but yes, that is a very valid simulation to try out. We did not try it out yet, yes.
Is it still converging to whatever that epsilon?
I did not try it, but I think, like, if you use an estimate of tau hat mix, it will probably again go down as 1 over square root t, right? Where if you use t samples. So I think it should not mess up the bounds too much. But again, this remains to be seen. I haven't done the simulations to check what happens, but I presume
The eigenvalue, you estimate something or just use something.
for the eigenvalue, it's trickier because, like, it's not just the smallest entry of the stationary distribution, right? It gets sort of, it depends on the feature matrix also. But because you know the feature matrix, you can probably use it to get some bound on omega. So these I haven't tried out, but these are legitimate questions. Yes.
Maybe I have one more question.
Yes.
So you are using, it looks like, I think that was also your open problem where you say that you have too much memory requirement. So
Yeah.
if I understand correctly, in your estimator, you are using this y0 to yt.
So it will grow with the horizon. So it's linear in the horizon. So if I wait till like t iterations for each of the k components, where k is the dimension of the feature vector, you will need the entire history basically. But the good news is that there are more recent results on robust mean estimation with streaming data. So, and I think you could potentially, under some assumptions, get away with logarithmic in the horizon, which would be an huge improvement, but these are very recent results, so I need to look at them. Okay. But right now, it's as I said, I mean, this is a big limitation that we do require a lot of memory for this algorithm.
Okay,
Yes.
thank you.
Just a quick follow-up question. So this robustness part, in principle, can it be combined with tail average and get rid of the... Are you so tied to your simple proof?
No. So good question. Actually, the simple proof doesn't work here.
Yeah, okay.
And the reason is that the disturbance in the first part of the proof was ordered alpha squared. In the second part, it's ordered alpha. And I cannot use the same proof technique for the second part.
Okay.
So in fact, it doesn't even go through that same proof technique.
In principle, any TD proof can be tried.
Potentially, yeah. Yeah. So yes, tail averaging could be useful there. Yes.
As a token of appreciation from the conference organizers, which is not me, I'd like to thank Professor Harithamitru.
Thank you so much. Thank you. Oh, yeah, sure. Thank you so much.
So, move on to the next talk. I think I don't need this.
Yes.
So, the third talk before we break for lunch is by Professor Ashish. I think it's green. Okay, am I audible? Yeah, okay. So, Professor Ashish Hota received his BTech and MTech both from IIT Kharagpur in 2012 and the PhD from Purdue in 2017, all in electrical engineering. He was a postdoc at Automatic Control Laboratory in ETH Zurich in 2018. He is currently an assistant professor with Department of EE in IIT Kharagpur. Among his recognitions are a young associateship of INEE, outstanding graduate researcher from Purdue, and the Institute Silver Medal from IIT Kharagpur. His research interests are in areas of stochastic optimization, game theory, and control of network systems, which probably include reinforcement learning. Today he'll be talking about some fixed time convergent gradient flows and fast evasion of non-degenerate saddle points. Off to you, Professor Ashish Hota.
Thank you very much.
Okay. So good morning, everyone, and many thanks to the organizers for inviting me to talk about some of our work. So this talk is about So this talk is about using ideas from control theory to design and analyze continuous time algorithms for solving optimization problems. And this is joint work with Dr. Mayank Baranwal, who is a senior scientist at TCS Innovation, and two of my former undergraduate students at IIT Kharagpur, Param and Vishal. So optimization algorithms lie at the heart of many AI and machine learning problems. These algorithms often are iterative in nature. So we start with an initial candidate solution. Then we find out some information about the function near that solution. For example, the value of the function, the gradient of the function, or the Hessian of the function. And based on this local information, we find the next candidate solution and so on. So naturally, most of the analysis forms are from the point of view of a discrete time viewpoint. Now, an alternative approach is to view these solutions are coming from a dynamical system and use ideas from control theory or dynamical system theory to analyze the convergence of these algorithms and potentially also come up with new algorithms. So this philosophy has been tried out not only in the case of optimization, but also in the context of reinforcement learning as well. Now, in this talk, we will talk about unconstrained optimization problems, not specifically reinforcement learning, but the hope is that some of the ideas that I will present today maybe will be taken up by you to analyze reinforcement learning problems as well. Okay. So let us look at the classical unconstrained optimization problem, where we are minimizing a cost function f of x with respect to variable x. Now, the gradient descent scheme looks as follows. So we start with an initial candidate solution x0 and we update it as follows. So we find the next iterate as the current iterate minus some step size times the gradient at the current iterate. Now, if we take the continuous time limit of this, we obtain what is called the gradient flow. So x dot, that is dxt by dt, equal to negative of the gradient of the function. Now, if the function is well behaved, that is, it is strongly convex and so on, we can show that the gradient flow converges to the optimal solution asymptotically. But the problems that we will tackle in today's talk are, can we design some modification of these continuous time gradient based algorithms to find optimal solution in a fixed amount of time, regardless of where we start. Then we will see that are these algorithms robust to perturbations and can they evade saddle points and so on. And then we will also extend these algorithms to make them faster, potentially inspired by momentum type of ideas, and then try to see whether they can solve minimax problems. And finally, I will also illustrate how these algorithms perform in various machine learning tasks, including training of neural networks. Okay. So remember, I mentioned the word convergence in fixed time. So let us see formally what it means. So this is a result by Polyakov from 2011. So the formal definition is as follows. So let us say that we have an autonomous differential equation or dynamical system given by x dot t equal to g of xt. Now let x star be an equilibrium point of this dynamical system with g of x star equal to 0. That means when x of t arrives at x star, then x dot becomes 0 and it remains at x star forever. Now such an equilibrium point is said to be globally fixed time stable if it is stable in the sense of Lyapunov, and there exists a uniform settling time t bar such that no matter where you start, regardless of your choice of initial condition, xt is going to be equal to x star for all time greater than equal to t bar. Okay, so that means sometime before t bar, xt is going to converge to x star and it is going to remain there forever. So let me sort of visually illustrate the different notions of stability of equilibrium in dynamical systems. So let us consider an example in R2. So there are two states x1 and x2, and let the x-axis be like the time axis. And let us say that 0 is an equilibrium point in this case. Now this equilibrium point is said to be stable if you give me any epsilon, then I can come up with a delta such that if you start from any point which is within distance delta from the equilibrium point, then the trajectory is always going to remain bounded within distance epsilon from the equilibrium point at all times. Now if it happens that the trajectory converges to the equilibrium point as time t goes to infinity, then we say that the equilibrium is asymptotically stable. And if it converges exponentially quickly to the equilibrium point, we say that it is exponentially stable. And the notion of fixed time stability says that there is a finite time t bar such that no matter where I start, the trajectory is going to converge to x star before that time point. Okay. Now often the primary tool to use stability or prove stability of these dynamical systems is by constructing a Lyapunov function. So these functions look like this. At the equilibrium point, the function value is 0, and at all other points, the function value is strictly positive. And the time derivative of the function value, dv by dt, which if you use the chain rule, is the gradient of the function times dx by dt, should be less than equal to 0 or sometimes strictly less than 0 and so on. Okay? So depending on how strong this is and how quickly the function value decays, you have any of these results. Now, how can we extend this to prove fixed time stability of an equilibrium point? So the lemma that we are going to principally use in our results states the following. So let us say that we have a Lyapunov function which is continuously differentiable. At equilibrium point x star, the value of the function is 0, and at all other points, the value of the function is strictly positive. And the time derivative of the function is less than or equal to 2 terms, both of which are negative. And both of the terms look like some constant times v of xt to the power gamma 1 and another constant times v of xt to the power gamma 2. And gamma 1 is required to be between 0 and 1, and gamma 2 is greater than 1. So the idea is that if v of xt, its own value is, let's say, larger than 1, then if we amplify it by choosing gamma 2 greater than 1, then this fellow becomes large, and due to the negative term, the Lyapunov function value decays faster. Now, if I did not have the first term here, then after the Lyapunov function value becomes less than 1, the decay is not going to be fast enough. So therefore, we have the first term here, and here the exponent is between 0 and 1. So therefore, when the value of the Lyapunov function is less than 1, if I have an exponent which is smaller than 1, then the faster decay rate somehow gets maintained. So think about x square and square root of x between 0 and 1. So below 1, we need the exponent to be smaller than 1. So if we are able to construct a Lyapunov function for x star which satisfies this, then x star is globally fixed time stable. And we also have a closed form expression of the upper bound t bar in terms of the parameters a1, a2, gamma 1 and gamma 2. Okay. All right, now let's come back to the problem at hand. So we are going to use the fixed time stability theory to come up with algorithms, continuous time algorithms for solving an unconstrained optimization problem that looks like this. and the function f needs to satisfy the following assumptions. The first is that the function should be continuously differentiable with locally ellipsis continuous gradients. The function should attain the minimum value at x star, that is, and the minimum value is f star equal to f of x star. The function has a unique minimizer at x star, and the function satisfies the so-called PL inequality, which requires this condition to be satisfied. So the gradient of the function square should be greater than or equal to 2 mu times fx minus f star. Now we do not require convexity. So if a function happens to be strongly convex, then it satisfies PL inequality. But there are functions which are not convex but also satisfy PL inequality. But we also require the function to have unique sort of minimizer, which is kind of sort of a limitation, you could say. Okay, so now let me present the first algorithm which finds the equilibrium point in fixed time. So this is an algorithm introduced by Garg and Panago in 2021. So it looks like the following. So it looks very much like gradient descent, but we have two terms here. And in the gradient term, we normalize by a norm of the gradient to the power of some quantity. Now in the first term, we have the exponent p1 minus 2 by p1 minus 1. And in the second term, we have p2 minus 2 by p2 minus 1, where p1 is required to be greater than 2 and p2 is required to be between 1 and 2. And we will see why these requirements are there when we go through the proof. Now the theorem says that when the function satisfies assumption 1, then the flow given by this equation converges to the optimizer x star in fixed time, regardless of your initial solution x0. Okay, so let us proceed. Now, first we have to conjecture, a candidate Lyapunov function. So there are different ways in which we can come up with Lyapunov functions. One example could be that Vx equal to x minus x star norm square, or the gradient of fx norm square and so on. But this is the one we pick, which is just fx minus f star. So since we have a unique minimizer, then at x equal to x star, the value of the function is 0, and at all other points, the function value is strictly positive. Now let us take the time derivative of this. So the time derivative is going to look like, if you apply chain rule, the gradient transpose x star, and in place of x star we substitute the dynamics we defined on the previous slide. Now the gradient term would go here, we would have norm fx square, and then if I do 2 minus of this exponent, then these are the terms which I am going to come up with. Now remember, our goal is to show that v dot x is less than or equal to some constant times bx to the power gamma 1 minus another constant times bx to the power gamma 2. Now, in order to get the Lyapunov function, I need to somehow get rid of this gradient and get my fx minus f star. Now, in order to get that, I will use the PL inequality, which is very convenient in this case. So I will just replace the gradient with this particular term here, and that is sort of very easily, with its bit of algebra, gives me that what I require. That is, v dot is less than or equal to some constant times b to the power gamma 1 and another constant times b to the power gamma 2. Now remember, we required one of these exponents to be between 0 and 1 and the second exponent to be greater than 1. And in order to achieve that, we need to set p1 to be greater than 2 and p2 to be between 0 and 1. So once we have all of this, then we have satisfied the conditions for lemma 2 for fixed time stability, and therefore we can now say that the solution of the differential equation that I presented would converge to the optimal solution of the optimization problem x star in fixed time with the upper bound and the time given by this expression. Okay. So the proof is quite short and quite intuitive, but hopefully it was easy to follow. Okay. Now let us proceed. So we will now see that what happens if there are some additive perturbations that are affecting this dynamics. So we make some assumptions about the nature of the perturbation. Essentially, we assume that the norm of the perturbation is less than or equal to some constant times x minus x star whole square. Now this is a simplifying assumption, but essentially what it does is that it preserves x star to be the equilibrium point of the perturbed dynamics as well. We don't want to perturb it so that the x star is no longer the equilibrium point. Okay. Now, under the previously stated assumptions and some additional conditions on the parameters, for example, 2 conditions are required, that is 4 mu square and minimum of C1 and C2 should be greater than L. P1 can be greater than 2 as before, but P2 needs to be between 1 and 1.5. Now, under these conditions, the equilibrium point x star can be shown to be fixed time stable as before. Okay. Now, we have been talking about these continuous time algorithms, but in practice, these need to be implemented on a digital computer. So therefore, they implicitly have to be discretized at some point in order to numerically compute the optimal solutions. Now, the term consistent discretization refers to the analysis of these discretization ideas. So basically, we want to discretize the dynamical system in such a way that the discrete version, the solution under the discrete version remains close to the solution under the continuous version. So there are different notions of these discretization. One specific example is what is called as t comma epsilon discretization. Here the idea is that if I take a time window between 0 and t, and there is a epsilon is a small constant, and I discretize that time window into a finite number of sort of points, then any continuous time I pick from this window, I should be able to find a discrete time point such that the solution of the continuous ODE and the discrete implementation of that remain bounded within an error epsilon. And I can also do the vice versa. If I pick a discrete time instance, I can find a continuous time in the neighborhood such that this is achieved. Now, we sort of tried to show whether the fixed time gradient flow introduced before admits such a consistent discretization. Specifically, we looked at the forward Euler discretization, which is written here. So the dynamics is discretized with a step size eta, which is a small constant. And our theorem says the following. Now, if the function satisfies the previously stated assumption, and P1 and P2 satisfy both of these conditions, so that is P2 can be anything between 1.5 and 2, and P1 needs to be picked such that this equality is satisfied. Then, no matter which epsilon you give me, there exists an eta star such that if I pick the step size eta to be between 0 and eta star, then the trajectories of the discretized system is a T epsilon discretization of the original dynamical continuous time system. And not only that, the iterates generated by the discrete implementation converge to the optimal solution in the following sense, that there exists a finite time instant k star, which is finite, such that the iterates would converge to x star within error epsilon within time k star. Okay? And the important thing to note here is that k star does not depend on your choice of initial solution. So no matter which initial solution you pick, if you run this algorithm for time longer than k star, you would be within distance epsilon from the optimal solution. And the convergence rate is not geometric or exponential, it sort of follows like a tan kind of a curve. So if you recall, tan at pi by 2 is infinity and then comes to 0. So here the upper bound starts at infinity at k equal to 0, but as sort of time proceeds, kind of converges to 0 in a manner that looks like the tan function. Yeah. Okay. So now, so far I have talked about the proof and some of the properties of the fixed time stable gradient flow. Now I'm going to propose a modification of the gradient flow with the hope that it evades saddle points that are often present in many non-convex optimization problems. Now, past work has shown that gradient-based algorithms can evade these saddle points, but they often spend a lot of time in the vicinity of the saddle point, slowing down convergence to the optimal solution. Now, recent works have also shown that if you use gradient descent but normalize the gradient element-wise, then convergence to the optimal solution is faster. That is, these algorithms escape the saddle points relatively quickly. Now, motivated by these past works, we propose a gradient flow scheme with element-wise normalization that escapes any neighborhood of a saddle point in a fixed amount of time. Okay. So let us see that. So here is the normalized gradient flow, which we term gen flow. So now I am writing the dynamics element-wise. So the ith element of the solution vector evolves in a continuous time as follows. So it kind of looks the same. So earlier the denominator had the full gradient norm to the power of p1 minus 2 by p1 minus 1 and so on. Now here for the ith component of the solution vector, I am normalizing it with the ith component of the gradient vector raised to the exponents. So earlier we had the full norm of the gradient. Now I only have the ith component of the gradient normalizing it. And as before, I require P1 to be greater than 2 and P2 to be between 1 and 2. Now the theorem states that this particular continuous time algorithm converges to the optimal solution of the optimization problem in a fixed time independent of initialization. Now one of the key lemmas that will be used in the proofs for this part of the talk, which we call the power inequality, it says the following. Let us say that we have a vector z in Rn. Then if I look at summation of all the components raised to the power p, then it is less than or equal to summation of the components, each component raised to the power p, if p is between 0 and 1. And when p is greater than 1, we have an extra term which now depends on the dimension of the vector n. Okay. Now with this, let us try to prove the convergence of the Genflow scheme here. So as before, we pick the Lyapunov function to be fx minus f star. We calculate the time derivative. Now I am writing things component wise because I have used component wise normalization. Now as before, if we write x star and then take the gradient inside, square, and then take 2 minus the term in the denominator, this is what I will end up with. But this is not what I want, because I want to show that v dot is less than equal to some constant times the Lyapunov function to the power gamma 1, and the Lyapunov function depends on fx. Now to use PL inequality, I need to have the full gradient in some way, and in order to obtain that, we use this power inequality lemma here. So both of these terms, we kind of use the power inequality, where this kind of mod component wise, we take it over the entire gradient vector, and once we have it, we apply the PL inequality to get the 2 mu times fx minus f star, which is my Lyapunov function. Okay. Now with this manipulation, we can show that we have now come up with a setting where we satisfy the requirement for the equilibrium to be fixed time stable, and we also obtain the upper bound in terms of these new parameters. Okay. Now let's look at the problem of evading saddle points, which motivated us to design the element-wise normalized flow to begin with. We consider functions now that are twice continuously differentiable. Now for such functions, a point x star is a non-degenerate saddle point if the gradient vanishes at that point, but the Hessian is non-singular. So it's neither a minimizer nor a maximizer. Now it also has the property that there exists some eigenvalues of the Hessian where lambda is negative, which means that local improvements are always possible. So there are some directions which will give me smaller values of the function if I follow those directions. Okay. Now our main theorem here states the following. Suppose we have the function f which satisfies the previous assumption. Let x star be a non-degenerate saddle point of the function, and let xt be the solutions generated by the Genflow scheme. And the initial condition is such that xt does not converge to the saddle point. So there may be initial conditions which would converge to the saddle point, and of course we cannot escape them, but therefore we assume that x0 be an initial point where the solution starting from x0 does not converge to the saddle point. Then we have the following upper bound on the time that the algorithm spends in a certain neighborhood of the saddle point. Okay? So let's say that R be such a neighborhood, and let's say that R is a sufficiently small constant. Then the time spent by the algorithm in a neighborhood of radius r around the saddle point is upper bounded by this constant here. Now the constant is the minimum of 2 terms. The important thing to note here is that both these terms has a product which depends on r, and there are some other constants which do not depend on the size of the neighborhood. These other constants are some constants between greater than 0.5, less than 1, and the largest eigenvalue in terms of the magnitude of the Hessian matrix and the smallest absolute value of the eigenvalues of the Hessian matrix. Now if you recall, we assumed that P1 to be greater than 2 and P2 to be less than 1. So one of these terms is an increasing function of r and the other term is a decreasing function of r. So that means we are taking the minimum, so one is an increasing function, another is a decreasing function. So if we find the point at which both are equal, so that is going to act as an upper bound for both of them. So let r hat be the constant at which both the terms are equal, and therefore we can now obtain an upper bound which does not depend on the size of the neighborhood but only depends on r hat, which is the solution of this complex looking equation. Okay? So essentially we could upper bound the time spent by the algorithm in the neighborhood of the saddle point, which does not depend on the size of the neighborhood. But of course the neighborhood r should be sufficiently small, it doesn't capture the entire space. Okay? All right. Now we also sort of modified the GenFlow scheme in a couple of directions. First we looked at sort of a version which trying to capture momentum type terms in the optimization algorithm. So we add a new set of state variables v, also of size n, and then bi dot evolves in this manner and xi dot evolves in this manner, and p1 is greater than 2 and p2 is between 1 and 2 as before. Now the equilibrium point of this is for the b part it is 0 and for the x part it is x star. So when x equal to x star and b equal to 0, we obtain vi dot equal to 0 and xi dot equal to 0 for all I. And we can prove that this new modified scheme, which we term GenFlow M, converges to 0 comma x star in fixed time independent of initialization. Okay. Now the Lyapunov function for the x part is fx minus f star as before, and for the b part, because the equilibrium point is 0, we just have a simple quadratic. Now if we write out the time derivative, we obtain the first equation, and then we substitute the dynamics of xi dot and vi dot and then obtain the second equation after some cancellations. Then we use power inequality twice, and finally after a bit of algebra we obtain that b dot is less than equal to some constant times b to the power alpha and another constant times b to the power beta, where alpha is between 0 and 1 and beta is greater than 1. So this satisfies the requirement that the equilibrium point is globally fixed time stable. Okay. Now the last theoretical result I will present today is that we are going to tackle a minimax problem. So we have a function g, which is a function of two variables x and y, and we are trying to minimize g with respect to x and maximize g with respect to y. So earlier we were trying to evade saddle points, which we did not want to converge to them. Now we are trying to converge to the saddle point because we want to converge to the saddle point. Now these kind of problems arise in many settings, for example, two-player games, or if you are trying to design primal dual algorithms for solving constraint optimization problems, and so on. Now here we require the function to be strongly convex in the x with respect to x and strongly concave with respect to y. So we do require convexity here. So PL inequality is not enough. And let the strong convexity concavity parameters be given by mu1 and mu2. And we propose the saddle point dynamics given by this. So xi dot is equal to gradient of g with respect to xi, but normalized with respect to the complete norm of the full gradient with respect to both x and negative of the gradient with respect to y. So we stack them, we get the delta g vector, and we normalize both xi dot and yj dot with respect to the full gradient. Okay. Now the theorem says the following. So if the function is strongly convex, strongly concave, then the saddle point dynamics converges to the unique min-max solution in a fixed amount of time independent of initialization. Now here we cannot use the Lyapunov function fx minus f star anymore. So the Lyapunov function now looks like half of gradient of g with respect to x square plus half of gradient of g with respect to y square. Now if we take the derivative here, so we obtain sort of different terms. The cross terms can be shown to cancel with each other. Now we are left with terms that only depend on the gradient and Hessian with respect to x and gradient and Hessian with respect to y. After that, we use the fact that the function is strongly convex, strongly concave with respect to parameters mu1 and mu2 to obtain the first inequality. Then we take the min of mu1 and mu2, take delta g inside, and we have this. And then finally, this is the Lyapunov function was the gradient, so we have the Lyapunov function here. Okay. So once again, we arrive at an inequality which satisfies the sufficient condition for fixed time convergence. Okay. So to conclude, I will present a few numerical results. The first one is a function called Rosenbrook function, which is a non-convex function, which has a global minimum at 1, 1, but around 1, 1 there is a long valley. So often sort of gradient-based schemes get stuck in the long valley and make very small progress. And we can also show that this function satisfies PL inequality with modulus 0.1 in the region -1, 1 to 1, 1. And the performance of different algorithms look like the following. So we compared Adam, Nesterov's accelerated gradient descent, the fixed time stable gradient flow, and the momentum version of that. And this is how it looks like. So in about 1500 epochs, the fixed time stable flow with momentum has kind of converged to a very small value. Others are making progress, but the progress is relatively slow. Now the second plot shows that if I start from many different initial points, I should ideally converge to the optimal solution in about the same time, because we said that theoretically, no matter where you start, you should converge to the optimal solution in time that is independent of the initial point. And we kind of see that here as well. Now this is implemented by discretizing it using Euler discretization with a very small step size. You could of course use your favorite ODE solvers, you may get even better results. So we would have naturally probably stopped there, but our undergraduate students are very fond of training neural networks, so they try to train that. So the first result here shows that we compare the performance of the element-wise normalized gradient flow scheme and its momentum version with benchmark algorithms such as Adam, SVRG, RMS prop, and so on, in training a neural network for an image classification task on the MNIST dataset, which contains handwritten diseases. So this is the detail of the architecture. So we used a single convolutional net layer with ReLU activation, followed by a dense layer. And then finally, the output layer transforms this large input to a 10-dimensional output with softmax activation. And for the scheme we proposed here, we chose P1 to be 10, which should be greater than 2, and P2, which should be less than 2, to be 1.98, and discretization parameter 0.01. Okay. And we also tuned the hyperparameters of the other algorithms accordingly to obtain good performance. Now we compare the performance along 3 metrics. So the first is the training cross entropy loss, and as you can see, the blue line here corresponds to the momentum version of our method, and also sort of other algorithms are also there. So we have some superior performance, and also performance is generally competitive. And we also looked at accuracy over the training dataset and accuracy over the testing dataset. So the proposed algorithms with suitable discretization performs competitively compared to Adam and other standard solvers for neural networks. Finally, we also looked at training of generative adversarial networks, which are min-max problems. Again, we used the MNIST dataset for this purpose, and as you can see here, the accuracy on the dataset of the proposed algorithms such as GenFlow, GenFlow-M, and FXTS sort of performs quite well with respect to the algorithms here. Now, these are some of the images that are generated by these algorithms. So this pretty much look like the ones you see in the raw dataset as well. So I'm not saying that our algorithms are always performing better, but the performance is competitive in a variety of tasks. Yeah. So I think one result I skipped here. So we also looked at the point about evading saddle points. So we consider this test function, it's a function of both x and y. It has 3 critical points, 0, 0, 0, -1, and 0, 1. So the first one is a non-degenerate saddle point, and Z2 and Z3 are isolated local minima. And if you look at the algorithm at different epochs, at iteration 25, as you can see that the element-wise normalized flow has been trying to make progress towards the local optima from both sides, but the gradient descent is kind of stuck. If you give more time, so the normalized flows have almost converged, and gradient descent, which is the green one, is somewhere over here, and after 200, green is finally making some progress. But the proposed normalized fixed time stable flows have made progress much before the green line, which is the gradient descent. Okay, so to summarize, we analyzed the convergence of fixed time stable gradient flow and showed that it is robust with respect to additive perturbations, satisfying some conditions, and that it admits a consistent discretization. We proposed element-wise normalized version of the scheme, show that it also converges to the optimal solution in Okay. Okay. Yeah, we showed that the escape time from the saddle points can be bounded, and we also showed fixed time convergence to solution of min-max problems. And finally, we also had some experimental results showing that these algorithms perform quite well compared to other standard approaches. So there are various directions for future research. For instance, we can sort of try to find consistent discretization strategies for the normalized flows, possibly under additional assumptions such as Lipschitz continuity of the cost function. We can also try to extend the proposed saddle point dynamics to include a momentum variant and analyze variance reduction properties and robustness of the proposed algorithm to noisy gradients and different types of noises. And finally, we can try to extend these ideas to distributed optimization, Nash equilibrium computation and networks, and reinforcement learning. So I've seen some work on fixed time stable flows for distributed optimization and Nash equilibrium seeking, but I have not seen a lot of work in the context of reinforcement learning, and hopefully this talk will motivate some of you to take it up in future work. Okay, so this concludes my talk. So further details are available in these two papers, and we also have a PyTorch implementation of our optimizer which can be found here. So I sort of encourage you to try it out and compare it with other standard optimizers such as Adam and so on. Okay. So this concludes my talk, and thank you very much.
Obviously, I cannot ask question on the mathematical equations. So this concept of fixed time convergence is something new to me. And you also said like this is yet to be applied in RL also, right? Am I right?
I have not seen any work personally. There may some exist out there, but I don't know. Yeah.
So is the idea of like a fixed time is something learned, or like the number of iterations is like
So it's basically sort of in optimization as well as in RL. So we have we can approximate the discrete time iterative algorithms with a continuous time ODE, like Professor Borker's work and so on. So now if we have a continuous time dynamical system, there is a notion of fixed time stable equilibrium points which requires stronger conditions on the Lyapunov function than just asymptotically stable equilibrium points. So if we can find a Lyapunov function which satisfies the stronger requirements given over here, then that particular equilibrium point is fixed time stable for the continuous time dynamics. So now there are two parts here. First is to come up with a Lyapunov function which satisfies this for your equilibrium point. Second is to make sure that when you are discretizing it while implementing it on a computer, you do it in such a way that the fixed time property is kind of preserved. So there are two challenges here. If both are satisfied, then yes, we can go ahead and use that. Yeah.
not necessarily tied to the number of episodes?
No, so it's more of like, for example, the TD update or Q update. First, we have to approximate that with an ODE and then try to run it. Now, while executing it as in a discretized manner, it would look like discrete time iterates, and at that time we would use whatever episodic or experience replay and whatever technique we want to use. Yeah.
Thank you.
Yeah.
Yeah, hello sir. Hello. Hello.
Yeah.
So generally, when you are doing the experimental setup, so you are using the neural network with the ReLU. So the assumptions in the beginning when you showed, does that satisfied by the neural network?
So there may, okay, I don't know whether all of these assumptions are satisfied. Probably not satisfied, but we found some references which say that in some cases, certain types of architectures, the loss function, if you can choose in such a way that it may satisfy PL inequality. So it depends on how you choose it. But in general, no, it generally is not satisfied. Yeah, yeah. Okay, okay.
Like sir, not only ReLU, like different activations are there. So does everything will satisfy this kind of?
No. Yeah. I don't know. I haven't checked. Yeah. But as Professor Vidyasagar is saying, ReLU satisfies it. Yeah. Okay. Yes.
Yeah, thank you.
I had a similar point here. So, I mean, the thing is that in all of these proofs, you have some conditions to establish these very nice results. But
yes,
in the GANs or the NNs, you just tried it and it seems to give very good results. Is that how?
Yes, but that's also how most of the neural network training algorithms are implemented. Yeah.
Okay.
Yeah.
So one question from my end. See, before even talking about reinforcement learning, so it appears that you are proposing acceleration idea, right? So do you have any evidence of acceleration in stochastic settings using this thing? Like, is there any work that says, in a stochastic setup where the measurements are not readily available, this idea can actually lead to some sort of acceleration?
We do not have proofs with regard to that.
But is there even empirical evidence?
Well, empirical evidence are the ones that we showed here. So these are in training neural networks. Sort of seems to be performing sort of competitively compared to the standard neural network training algorithms. And the robustness result we showed is very tailor-made. The additive perturbation needs to be sort of have quadratically bounded with respect to the distance from the optimizer. So if you have other kinds of noise, let's say you have, instead of the gradient, you have gradient plus some constant, these cases have been challenging to analyze. We tried, but we could not succeed. Yeah.
Okay.
Yeah.
Hello? Am I audible?
Yes.
Sorry. So, nice talk. I've been working in the same direction for fixed time stability in my work. So, my question is, you have used only for classification problem, right? The current examples are.
Yes.
But however, if you go into the dynamical system where you wanted to work for optimal control problem.
Okay.
So, in that case, you have temporal as a component in your entire dynamical system. How well your algorithm will scale up to them?
So you mean settings where it's an optimal control problem and your dynamics appears as a constraint in the problem?
Yes.
Yeah, these cases, I don't know. But there is another line of work which talks about online feedback optimization. So what they do is that instead of having the dynamics as a constraint in the optimal control problem, they try to have an interconnected set of dynamical systems. So on one layer, you have the gradient descent kind of a step, and in the second layer, you have the dynamics. Now what happens is that if you have a nonlinear dynamics, which is an equality constraint in your optimization, the problems becomes computationally intractable. But instead of doing that, you kind of try to take a gradient step, apply it to the system, and then look at let the physics solve the solution itself, and then feed it back. Now, if you can show that both are interconnection of, let's say, passive systems, for example, then you can have nice results about convergence to the optimal solution. Okay. So there is some line of work which is around that.
Okay.
Yeah.
Thank you.
Yeah.
So you can go back to the Polyak-Lovacevic condition.
This one, right?
No, Polyak-Lovacevic PL condition.
Yes.
Yeah, so F star is the minimum value, right?
F star is the minimum value.
Yeah, so what that says is that every critical point is a global minimum. That in
Yes.
general won't be possible unless it's a unimodular function.
Right.
So it's quite restrictive.
Yes.
Typical, no other local minima, no saddle points.
The unique minimizer may have saddle points, but okay.
No, if you have unique minimizer, no. If you have two minimizers,
Okay.
for example, if you have two values, and
Right,
suppose
right.
it's a coercive function going to infinity, and
It,
you go to
yes,
infinity,
yes.
there has to be at least one saddle point in between.
Right,
called
right.
mountain pass lemma.
Right.
So unless it's unimodular, you are not going to get this, which is very restrictive.
Right. Yeah.
The other question I had is that it's a non-Lipschitz differential equation.
Yes.
So there are no well-positiveness issues. It may have
Yeah,
more
there are. So under some conditions in this particular paper, they showed that this dynamics, the solution exists.
No, it will exist, but
Yeah.
will it be unique?
If I recall correctly, they had a result about existence uniqueness.
It's not unique, you don't even know. I mean, it's a capital T may not be unique.
Right. But if I'll check, but I believe that they had results about existence uniqueness about the solution. Yeah.
Thank you.
Sir, I have a question. So, while discussing about using neural networks, you said that by customizing the architecture, you were able to get some of the assumptions satisfied, right? So,
No, we did not customize it like that. We took a very standard architecture. We used standard neural network optimizers, and then we also compared the performance with regard to our optimizer. Yeah.
so is there a possibility to use this neural architecture search to find an architecture that can satisfy all the constraints, like rather than anyway the ditto filters, all these like are handmade, like you design it, like you or somebody has designed and we're just using as such. So can we use neural architecture search to learn that configuration which will satisfy all the constraints, all the assumptions?
Possibly, I don't think I can answer it at this point, but it's a very good question. Maybe we can look it up. Yeah.
Thank you, sir.
Sir,
Yes.
so my question is, say my function has a lot of local minimizers. So does fixed time stability comes at the cost of being stuck in a local minimum? Are there any analysis in that direction?
Not that I know of.
Okay.
So I did a couple of questions. The first question is that in the case where you use momentum, can you show that the fixed time it takes for you to converge is smaller than in the case when you don't have momentum?
For some parameters, yes. Yeah, not all the time. Yeah.
I see. And the second question is that for stochastic optimization algorithms, at least in the discrete time, there are like known lower bounds for a given oracle model, right? So if you could in fact prove fixed time convergence, that would probably violate these lower bounds.
Okay.
After your discretization.
Right.
Isn't that right? Because you just get the like finite time. So it seems like it should not be possible for you to do this because that would probably violate these lower bounds.
Okay. Maybe I'll have to look into it. Yeah. But it's a very good question. Yeah.
Hello, sir. Sir, can you show me your assumptions slide? Sir, I think the neural networks do not satisfy the first assumption, sir. They are not locally Lipschitz continuous until you make an effort in the architecture to make it, sir. Still, your optimizer was able to perform well, sir. Can you comment on that?
I think that's a feature for any neural network training algorithm. So we don't have, many times the convergence results are obtained not for specific problem structures of neural network, but under suitable assumptions, and they tend to perform well for neural network training tasks as well. So that's also what we have tried to do. Okay. So these are sufficient conditions. So it doesn't mean that if these are not satisfied, the convergence will not happen. It's just that under these conditions, we have been able to achieve the proofs.
Okay, sir. Thank you, sir.
So other times may work, but the proofs are difficult and the tools can be
sir, also you said that you have published it as a PyTorch implementation, sir.
Right.
So why don't you just request original PyTorch to as a fork to just implement it in the basic library itself?
We haven't tried to do that. Maybe it's a good idea. We'll try to look into it. Yeah. Yeah.
Thank you, sir.
Thank you.
All right, so let's thank Professor Kota. As a small token of appreciation, may I hand this over to you.
Thank you.
Thank you.
Thank you. Thank you.
So we'll break now for lunch and we'll reassemble at 2 o'clock.